The prevailing dogmas may be right, but they still need to be challenged.
I found it an extremely useful principle in theoretical physics to adopt the Jesuit credo, which is that it is more blessed to ask forgiveness than permission.
Lawrence, can I ask a really dumb question?
Yeah, I'm biting my tongue, but go ahead, yes.
How do you have dynamics without time?
That's a wonderful question. I wish I had the answer. It's absolutely true that I can't, as a physicist now, adequately discuss what I mean by universes without time.
I don't know how to talk about dynamics without time.
Well, you can imagine, you can imagine,
Cosmology, as you know, is a subject that's changed a lot. You emphasize that, in fact. And I don't think it's over yet.
I think the essence of the scientific method is the willingness to admit you're wrong, the willingness to abandon ideas that don't work.
The world always needs heretics to challenge the prevailing orthodoxy. We're lucky that we can be heretics today without being burned at the stake.
What I'm trying to argue for is to think about things from a new point of view.
the question is time real? Does time have any objective reality? And of course it does.
That to know when you know and when you don't know and what it is you know and what it is you don't know, and it's you got to be very careful not to confuse yourself.
My sense is that the scientific way of thinking, questioning, some delicate mix of creative encouragement of new ideas and the most rigorous and skeptical scrutiny of new and old ideas, I think that is the path to the future, not just for science.
I can do a circle in space, right? But if time and space are really together as part of a four-dimensional universe, why can't I do a circle in time?
We should only talk about things that we can measure. Try to define things in terms of only things you measure. Or let's formulate the equation mathematically. Or let's guess the equation. Or all these things are tried all the time. That's very useful. But we all know that. That's what we learn in the physics classes, how to do that. But the new problem, where we're stuck because all those methods don't work. If any of those methods would have worked, we would have gone through there.
We have to be willing to challenge because we are in desperate need of change.
You could create a geometry where you could do a circle in time.
So when we get stuck in a certain place, it's a place where history will not repeat herself. And that's makes it even more exciting, because whatever we're going to look at the end, the method and the trick and the way it's going to look is going to be very different than anything that we've seen before, because we've used all the methods from before.
We've been exploring the idea of three-dimensional time. Three-dimensional time by no means is a new idea.
I have to ask, was there ever an idea that had more than one time dimension?
Yes, absolutely. So, Itzhak Bar was one of the people at USC who's pioneered this possibility. He has studied theories with two time dimensions. They're much harder to make work. I mean, if you have trouble thinking about extra dimensions of space, try thinking about extra dimensions of time.
Yet, three-dimensional time can be derived by using a set of new and peculiar equations. Let's suspend everything we know about time for a moment and use our imagination, if you will. Let's allow time to be a two-dimensional vector running in the direction of the arrow of time. We can assign this t1 coordinate to periods of time, and we can assign this t2 coordinate to present moments of time. If we allow the arrow of time to slide more towards the periods of time coordinate,
time moves by faster with more periods for present moments.
Or, if we move the arrow of time more towards the present moment coordinate,
we get more present moments per periods of time.
If we move the arrow of time so that it runs perfectly parallel with the periods of time coordinate, we end up with the past, present, future within a single moment. Or, if we run the arrow of time so that it runs perfectly parallel with the present time coordinate, we end up with an ever-present moment in a single period of time. The concepts of ordinary time and time dilation found in physics have equivalences in three-dimensional time which can easily be accounted for. Temporal events that happen on this side of the arrow of time correspond with the Lorentz transformation, where temporal events on this side of the arrow of time correspond with the inverse Lorentz transformation. These definitions give rise to temporal mechanics that, when applied to mass and energy, maintain conventional conservation laws.
What does it mean to talk about the origin of mass? In Newtonian mechanics, it really wouldn't mean anything at all. I teach students the three laws of motion, Newton's three laws, but before that, we discussed the zeroth law. And the zeroth law of mechanics, of classical mechanics, is that mass is conserved, that mass doesn't change. It's very basic to the very formulation of classical mechanics and was the great achievement of Descartes, Galileo, and Newton to realize the importance of introducing this primary concept of mass.
For these reasons alone, it is very important to introduce a temporal mechanical definition for mass that is consistent with classical physics.
The central equation of classical mechanics, F equals ma, which relates on the left-hand side of the dynamical concept of force to their motion through space and time, their kinematic quantity of acceleration. And to relate those two, you need some kind of conversion factor, and that's the role that mass plays. Something that didn't have mass, something that could give an origin to mass, wouldn't know which way to move. It would be a senseless object. Mass was a primary concept that couldn't be reduced to anything else. This all changed at the beginning of the 20th century when Einstein introduced his second law. It's called the second law because there's a familiar first law, E equals mc squared. This way of writing Einstein's law of the conversion of mass into energy suggests that perhaps it's possible to explain mass in terms of a different thing that could be primary, that is energy. And in fact, Einstein's original paper on the subject has this form of the equation.
A point particle mass has no spatial extension. Neither does the center of mass reference frame. For any object, regardless of size or shape, it has no spatial extension. We can treat mass as a negative volume of time, where t squared represents linear time with a one-to-one correspondence between periods and present moments, and minus t prime represents the negative passage of time. We can multiply in a variable n to increase or decrease the relative density or periods per present moments. A displacement in the passage of time would indicate acceleration. The fundamental equation of Newtonian physics, F equals ma, can be substituted with these relationships between temporal coordinates, giving rise to temporal mechanics. The temporal mechanical definitions for mass and energy are consistent with relativity. Applying them to the magnitude of some net force with a primary and secondary state, and applying the Pythagorean theorem, can be used to derive the inverse Lorentz function alpha. In this example, the primary state is the initial condition prior to acceleration. The linear time to passage of time variables have an inversely proportional relationship that can be set equal to 1. Since the acceleration term corresponds to a ratio between spatial and temporal coordinates, this becomes the expression for the primary state. In the secondary state, the linear time variables between the mass and acceleration terms are set equal. Since the linear time to passage of time variables have an inversely proportional relationship, the passage of time variable is proportional to the inverse spatial coordinate. Therefore, the secondary state represents to where and when the mass has been accelerated. Subtracting the primary state from the secondary state, we derive an equation in the same form as the reciprocal Lorentz factor, alpha, with the exception of units. Applying the right units to the spatial and temporal coordinates gives us beta, the ratio between velocity and the speed of light, turning our expression into the Lorentz function, revealing deeper insight into the relationship between space and time. Using 3 dimensions of space and 3 dimensions of time is much more dynamical, yet it still maintains Lorentz invariance.
More generally, in our theories of physics and the standard model, we understand things much, much better if masses are zero, and mass is somewhat of an embarrassment.
When mass is treated as a temporal scalar, the ratio between T1 and T2, or the slope of periods per present moments, can be skewed to account for time dilation, setting T squared equal to 1 using a reciprocal relationship between T1 and T2. This allows the rate of periods per present moments to change relative to Lorentz transformations and relativistic motion without affecting the passage coordinate. In this way, inertial mass can remain unchanged or Lorentz invariant, whereas momentum can undergo relativistic changes, increasing or decreasing. Mass can be treated as a 3-dimensional time scalar within a 4-vector metric. The temporally oriented 4-vector does not replace the standard 4-vector. Rather, these two metrics work together, consistent with standard notation and theoretical arguments. The temporal 4-vector is supplemental to contemporary physics, not oppositional.
I can do a circle in space, right? But if time and space are really together as part of a 4-dimensional universe, why can't I do a circle in time?
Temporal loops can cycle orthogonally in relation to the direction of the arrow of time. Though the passage of time coordinate and present time coordinate may reverse through half the cycle, linear time passes from the past through the present and into the future without change. Together, they form a dynamical relationship consistent with time-dependent phenomena in quantum mechanics, such as quantum electrodynamics. This temporal loop model is also consistent with the relationship between confinement and asymptotic freedom in quantum chromodynamics.
We should own up to the approximations being made. It's not quite true that the up and down quarks are massless. In order to account for some of the details of the patterns of masses, and in particular, technically for the mass of pi mesons, it's necessary to put in some finite value for the up and down quark masses. But it turns out that the finite values you need are only about 1% of the mass of the proton and neutron. So really, this is the origin of mass. Starting with QCD light, where there is literally no mass, we get 90% of the mass of the protons and neutrons. But that answer may not give you a warm and fuzzy feeling. One would like to understand in a more comprehensible way that would give some satisfaction from this marvelous result, where that mass came from.
The temporal definition of mass is very handy in cosmology. The temporal loop model can be extended into modern cosmology in several different ways, accounting for some of cosmology's unanswered questions.
Caltech professor Fritz Zwicky looked up to the neighboring Coma cluster of galaxies and observed something strange.
He could estimate the size and then obtain the mass in the cluster, and he found that it was vastly more massive than accounted for by the luminous matter.
Something didn't add up. The galaxies were moving too fast within the cluster for the amount of illuminated stuff he could see.
The subject remained dormant till Vera Rubin and Kent Ford measured galactic rotation curves.
Like Zwicky, her observations also seemed strange.
The only way to resolve this paradox of galaxies which spin 10 times too fast is to assume that there is a halo of invisible matter surrounding the galaxy, keeping the galaxy whole.
If this is a galaxy viewed edge-on, and you measure the velocity of gas going around the galaxy,
the gravitational acceleration due to a mass at the center would be m times g divided by the radius squared to the star, and that has to equal the acceleration, and the acceleration is the velocity squared divided by the radius. So this would then say that the velocity falls off like 1 over r. This is Kepler's planetary law. It's usually expressed in terms of the period rather than the velocity. Velocity falls like 1 over square root of r as you move away. That's not what was seen by Oort, and it's not what's seen by anybody since. What was seen is that the velocity is pretty much constant. Not the angular velocity, incidentally. It's not like this thing is rotating like a big giant pinwheel, but the linear velocity appears to be constant. So instead of saying all the mass is at the center, let's say the mass is distributed, and let's introduce a function m of r. M of r is the amount of mass contained within a sphere out to radius r. Not of a constant mass at the center, but a varying mass which varies like m of r. And in that case, v is constant, doesn't change with distance, and therefore we find that m of r must grow like r. M of r increases as you move away from the center. And so as you move out, this is not the mass density, incidentally. This is the total mass within a radius r, apparently increases linearly with r out to the outer boundaries of a galaxy, and even beyond that. At the moment, it looks like a piece of luck that the velocity curve is just flat. And I don't know a good, substantial, simple argument about why that's the case.
Three-dimensional time can be used to account for the anomalous rotation curves of galaxies without appealing to the presence of dark matter. The expression used in Suskind's example, where mass is a function of the radius, could be used in an alternative way to mathematically argue that there is an increase in the passage of time as the radius increases. For simplicity, we can substitute the basic temporal definition for mass with m, letting the variable n equal 1 for simplicity. Since we are dealing with a change in the passage of time relative to a gravitational field, as opposed to dealing with some mass, we can drop the minus sign. Since the t squared term is proportional with the units for g and v squared, only the passage of time term can vary. Therefore, the passage of time can be a function of the radius such that the passage of time increases with the radius consistent with Einstein's equivalence principle. This tells us that the relationship between inertial mass and gravitational fields can remain consistent, while the radius as a function of t prime varies with the distance from the center.
Dark matter's invisible presence is everywhere, or so it seems. Science has not directly proven dark matter particles exist. There are many suspects, but no answers. And observing something you can't see isn't easy.
Dark matter has yet to be detected. We haven't detected an actual dark matter particle. It has two very important characteristics. The first is that it does not interact with light, so it does not emit and it does not absorb light, and it interacts only through gravity. So how do we study dark matter? Well, one of the primary mechanisms we have for studying it is through its gravitational effects.
If you scan the sky with a powerful telescope, you'll discover that in certain directions, the image is distorted. It's as if you're looking through a very big droplet of water.
Basically, the idea behind gravitational lensing is that you're looking at the light traveling towards us from a distant source. So in my analogy, the candle is a distant galaxy, and I'm an astronomer on Earth looking at this distant galaxy through my telescope. And in between us, there's a giant clump of dark matter. A wine glass can be an optical lens. And as I look towards this distant galaxy here, we see features like rings and arcs instead because the light has been deviated through the medium, through the lens. This is just a little illustration to get you to understand gravitational lensing a little more, that the shapes of the galaxies are distorted in this spherical pattern. We see a ring and we see arcs, and all these shapes are distorted.
The explanation is that gravity bends light.
And this is a nice picture of the concept. If gravity is bending light, the images you see get distorted. The problem is, or the remarkable discovery is, that the light is getting bent even where there's little or no visible matter. No presently known form of matter fits the bill for this other stuff. It might be better to refer to the cosmological dark matter problem as the excess acceleration problem.
Dark matter is an unfortunate name. The name sort of sounds like mystery mongering and sounds like a cover-up somehow. If we just talked about excess acceleration, which would be more accurate. What's actually observed is that things like stars and galaxies don't move the way they should according to the laws of gravity. There's some extra acceleration, as if there's more stuff that's exerting gravitational forces.
We have already examined how three-dimensional time can be applied to acceleration. Acceleration involves a temporal displacement, lessening the rate of the passage of time as the object begins to transversely move through space. Deceleration involves a spatial displacement, lessening the rate of the change through space, followed by an iteration of repeating diminishing lengths of space as the frame of reference concludes transversely passing at an increasing rate of the passage of time.
This is one of the most famous results from gravitational lensing concerning the evidence for dark matter. This is called the bullet cluster. A cluster of galaxies contains two visible components. It contains galaxies and it contains hot gas. The hot gas is actually a lot more massive than the galaxies are. It's actually two clusters of galaxies that have collided through each other. When we look at the different components, these are the galaxies. We basically see that the galaxies have passed through each other during the collision. However, when we study this system through gravitational lensing, we can demonstrate that most of the mass is located at these blue peaks here. We learn two things from this. One, there's a lot of mass that is unseen. We don't see it. And secondly, it doesn't interact with normal matter. Had it interacted with normal matter, it would have stopped and been slowed down here. We can compare the location of the stars and the galaxies and this hot gas that emits an X-rays, and we find that all the normal matter is located within the dark matter scaffolding. The normal matter is confined to lie within the gravitational potential wells that are defined by the dark matter.
If we apply the new equivalence principle to dark matter and dark energy, it becomes apparent that when we look at extremely distant objects, or when we look at extremely massive objects, such as galaxies, we're not only looking at 3 dimensions of space, we are also seeing 3-dimensional time. What about gravitational lensing, or dark matter halos?
How do you find something that is invisible in space?
Just as a lens bends light, a large mass in outer space, such as a cluster of galaxies, bends light traveling near it. This is known as gravitational lensing. The bending affects the light reaching us, distorting the image we see of whatever lies beyond the mass.
By tracing the battered light's path, gravitational lensing detected dark matter concentrated in the halos of galaxies.
And looking at the distortion of light as it goes through galaxies, we actually have maps of dark matter.
When people found dark matter, everybody wanted to know, well, what is it, you know?
If time is really 3-dimensional, affecting our observations of distant objects in space, then we really do need to take it into consideration. Using the temporal 4 vector, we can see that there's one space component to 3 temporal coordinates. Recall what each temporal component corresponds with, and how they relate to the temporal definition for mass. As t squared, or linear time, extends, both the period and present time components extend such that for any given moment, the slope between periods to present moments is 1. In this case, both the passage component and the mass are unchanged. The net effect of this is that the mass can be set over a single spatial coordinate for an extended period of time, such as a point particle mass. If we extend that spatial coordinate into being a vector of three-dimensional space, then that point particle mass can be spread homogeneously over some volume of space as well. In an odd way, the mass is in more than one place at the same time, even though that same mass is in the same place at more than one time. If we examine certain images taken of gravitational lensing, a familiar geometry comes to mind: Lagrange points.
It's helpful to think about these things in terms of where you'd want to put satellites into orbit. And a geostationary satellite just stays directly above the same point on the Earth because it's going around at the same speed as the Earth is rotating. But there's a subtlety here. What you're actually doing is a three-body problem. You've got the Sun, you've got the Earth, and you've got your satellite. And so the force that you have to think about isn't just the force of the Sun, it's the force of the combination of the Earth's gravity and the Sun's gravity. At this point, if you think about what the pulls of gravity is doing, the Sun is pulling you that way, the Earth is pulling you that way, so both of them are tugging you in the same direction. So the net pull on a satellite here is stronger than just the pull of the Sun. So that contributes the extra gravity you need to keep the satellite travelling at the right speed to keep up with the Earth. So the distance between the Earth and the Sun is about 150 million kilometres, and this L2 point is 1.5 million kilometres, but it's sort of 4 times further than the Moon is from the Earth. Okay, so we've got L4 and L5. Now they're the sort of slightly too subtle ones. So if you look at L4, so this is the one that's sort of ahead of the Earth. So the Earth's coming around this way. This stays permanently ahead of the Earth, and just the same for the L5 point over here, that it's pulled towards exactly this point. And if you think about Jupiter and the Sun as your two bodies, then actually there are a whole bunch of objects which are kind of trapped at the L4 and the L5 points. They're called Greek and Trojan asteroids. Generically, they're called Trojan asteroids. They don't actually collect at L1, L2, and L3 because it turns out those orbits are actually unstable, whereas L4 and L5 are actually stable points, which means that when stuff is there, it stays there. A little perturbation, it won't actually move away from the L4 or L5 point. So any pair of objects where in the region where those two objects are the sort of the dominant source of gravity, you can find these Lagrange points and these kind of trapping effects.
Strangely, there is a geometrical overlap between the location of Lagrange points and the distortion of an image by a galactic dark matter halo.
Images from the Hubble Space Telescope show a distant galaxy framed by 4 images of the same supernova, a kind of mirage that's been dubbed an Einstein cross. It's called gravitational lensing, and it's a common trick of the light that shows up in tons of deep space images. In this case, light from a distant supernova was warped on its way to Earth when it passed through a galaxy cluster, splitting the image into 4. It's been observed a few times with things like this quasar, but a Johns Hopkins University astronomer says this is the first supernova.
It is really quite remarkable that the first multiple image supernova was not a double or a triple, but an Einstein cross.
Space-time appears to act like a Bose-Einstein condensate, or a Beck, a superfluid where quantum entanglement occurs over long ranges.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. Each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that. If you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. This little wave packet over here can't tell whether it's this one or that one or that one. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system.
A Beck could allow the temporal 4-vector and spatial 4-vector to spread out homogeneously over more than one place at the same time, while in the same place at more than one time. A sort of temporal blob.
But it's kind of like a mass that keeps getting bigger and bigger.
More towards the center of a galaxy, relative to the gravitational field, there is a significantly lower rate of the passage of time. The rate of the passage of time relative to the Beck is at a higher rate than the rate of the passage of time relative to the galactic center, even though the Beck is cooler. Relative to the periods per present moments, the Beck is operating near the infinite momentum frame, primarily in the passage per present plane. This is analogous to a zero viscosity flow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
The propagation of gravitational waves should affect this Beck, creating a disturbance, sort of a billowing effect, similar to Lagrange points, but rather than points, blobs.
The blob. It's indescribable. Nothing can stop it.
These are just simplified examples of how three-dimensional time and the existence equations can be applied to the concepts of dark matter without introducing any new exotic particles. If we extend our temporal model out further and let the energy density of the vacuum correspond with a very high rate of the passage of time, since it is associated with infinitesimal mass, it can be associated with the infinite momentum frame. Therefore, it's reasonable to extend our model out and cover the observations of dark energy.
A few years ago, astronomers decided to use redshift measurements to measure the expansion history of the universe.
There's a kind of supernova that you can recognize by its spectrum, which is always the same brightness. If you measure how bright it is at peak, you can tell how far away it is. You can use the color of the supernova to tell you how much the universe has stretched. So that means that by the time it reaches us, it looks red. That's called redshift. And exactly how red it looks tells you how much the universe has stretched since the time of that particular supernova explosion. You can map out for each supernova telling you how far back in time it exploded, and you can find out how much the universe has stretched since that time. We ended up using some of the largest telescopes in the world to do this over a number of years. 10 years later, we actually had enough supernovae to do this measurement, and there were just a few options. One was that the universe was going to be slowing because all the gravity in the universe would slow the expansion, and option 2 was a little bit more dramatic. That was one where the universe slows to a halt and then collapses in a big crunch, and the answer turned out to be none of the above. We seem to be faced with some new component of the universe that we hadn't recognized before. Apparently the universe is dominated by perhaps a dark energy, which would be some energy spread through all of space that we've never identified previously. We still don't know what it would be, and that it could be perhaps powering the expansion of the universe to be speeding up. That's one possibility. Another possibility is maybe even more bizarre. It's possible that Einstein's theory of general relativity needs modification.
However, if we're going to use three-dimensional time to account for dark matter and dark energy, we're eventually going to have to face the big question. What about the Big Bang? How does three-dimensional time affect our observations of the Big Bang? Since the present time coordinate is not dependent on the periods of time coordinate, the concept of a beginning of time doesn't really make much sense. The conceptual point of origin, where space and time appear to have begun, is known as the Big Bang singularity. Here, space-time is reduced to a single point. On the other hand, when viewed through the lens of three-dimensional time, it becomes nothing more than a temporal vanishing point. It can be argued that modern cosmology is a collection of artifacts resulting from limiting time to a single dimension. The idea of a beginning or ending of time is nothing much more than a temporal vanishing point.
My name is Fred Hoyle. I am the inventor of the well-known words Big Bang to refer to the origin of the universe, But I'm afraid I don't really believe in the Big Bang. I'm, generally speaking, not a believer in popular theories.
So what are the mathematical assumptions that go into the Big Bang Theory anyway?
The Doppler effect has been the best explanation for why we see a redshift in distant light as we look further and further into outer space at more distant galaxies. This would suggest that galaxies are moving away from one another, indicating that the universe is expanding. On the other hand, what if light itself becomes redder as it travels over greater and greater distances through space, or due to some kind of unknown physical phenomena?
If we lived in an infinite, unchanging universe, the entire sky would be as bright as the sun. But the sky is dark at night, both because the universe had a beginning, so there aren't stars in every direction, and more importantly, because the light from super distant stars, and the even more distant cosmic background radiation, gets redshifted away from the visible spectrum by the expansion of the universe. So we just plain can't see it.
On the other hand, couldn't it be the case that light redshifts on its own after having traveled for vast periods of time? As an alternative to the Doppler effect, three-dimensional time can be applied to frequency, wavelength, and the speed of light, and successfully account for cosmological redshift.
Let's examine a moment of undisturbed travel of a single photon. The difference between the final mass and the initial mass of the photon equals 0. There is no change in energy or momentum of the photon as it travels, undisturbed for a period of time. So that the mass of the photon doesn't change in order to maintain the conservation of energy, the passage of time must decrease proportionally as the period of time increases. Since there is a change in the period of time for a single photon, the passage of time decreases relative to the observed frequency of the traveling photon, and the photon appears to have increased wavelength. The period of time for a traveling photon increases proportionally with distance. Since the passage of time decreases as the photon travels through spacetime, the wavelength of the photon becomes longer relative to some observer in a non-relativistic frame of reference, say that of an astronomer billions of light years away.
Well, what about the expanding universe?
Now, it was Hubble in the late 1920s who made the observations of the night sky, which led us to see that our universe is expanding. So imagine a point so far out there that the average recession velocity is the speed of light. So that would form a sphere, which we call the Hubble sphere. The observable universe is larger than our Hubble sphere. It's actually limited by what's called the particle horizon. The observable universe has a radius of over 46 billion light years. The diameter is about 93 billion light years. And 13.8 billion years ago, everything in that volume and everything beyond it that we can't see would have been compressed into a tiny, infinitesimally small point that we call the singularity.
We can reinterpret the scale factor in the cosmological equation of state, the Friedmann equation, and apply it to 3 dimensions of time rather than 3 dimensions of space. We get a range of different rates of the passage of time over various periods of time per present moments spanning the history of the universe.
The basic question that we want to answer in cosmology is, what is the history of the universe? It really boils down to what is the time history of the scale factor.
Time plays a major role in cosmology and arguably is its most central concept.
The Friedmann equation says that a dot over a squared is equal to 8 pi g over 3 times rho plus maybe 1 over a squared or something. But it always comes in 8 pi g over 3. Lambda was introduced to get rid of this nasty 8 pi g over 3. It's called the cosmological constant. It was introduced by Einstein. It's also the thing which the newspapers call dark energy. There are basically 3 components to the energy density on the right-hand side. Let's call this matter, rho matter, is just the mass within that region, I guess I called it M at one point, the mass within the region, divided by the volume, rho, let's call it radiation, energy density in radiation, instead of being 1 over a cubed, is some constant divided by a to the 4th power. All right, there is a third component of energy, what I'll call rho naught, and that's vacuum energy, dark energy, cosmological constant, all the same thing. What I will tell you about it is it doesn't depend on A at all. It's energy that's there in the vacuum. It's the component which does not go to 0 as A gets bigger. In fact, you can think of it as a constant of nature. It's a number. It's there in the vacuum. I'm just going to write rho naught equals rho naught. It doesn't change. And it's A is equal to E to the square root of 8 pi g rho naught 3, I'm not going to write it, times T, exponentially increasing. Now with a little bit of work, you should be able to tell me how A depends on time for a given W. And you can find out how the universe expands for any value of W. With one exception. What's the exception? W equals minus 1, we'll see why, is exactly this vacuum energy here. If W equals minus 1, that says that the energy density doesn't depend on A at all. 1 plus W in that case would be 0, and we would just have C divided by A to the 0, and A to the 0 is just doesn't depend on A.
The scale factor for each component of the energy density of the universe can be substituted with a temporal scalar. This underpins the expansion of space as the explanation for cosmic redshift, conceptually replaced with the expansion of time. Notice that the scale factor for the matter density component is cubed. Since we are treating mass as a three-dimensional temporal scalar, we can reinterpret the scale factor for the matter density component as a temporal scalar. Furthermore, the scale factor for the curvature component can be reinterpreted as the one-to-one correspondence between periods per present moments defined as linear time. Finally, the scale factor for the radiation component, raised to the 4th power, comes from the Stefan-Boltzmann law expressing the scale factor as a function of temperature. There is an inversely proportional relationship between the passage of time and linear time relative to inertial mass and relativistic momentum. This is easier to understand when examining the expressions of thermodynamics and how they relate to temporal mechanics. In a closed-loop thermal system, such as an idealized heat engine, the inversely proportional relationship between temperature and the change in entropy can be used to set the heat engine into motion. Substituting the passage of time for temperature and substituting linear time for changes in entropy, the thermodynamic expressions for a Carnot heat engine can be used as a mechanism for the evolution of time.
Now think about this equation today, at the present time. How much of adding up to the right-hand side comes from radiation? How much comes from matter? How much comes from dark energy, lambda? And how much is left over in this curvature term? The ratios depend on time because they scale differently, but the ratios today are called omega. The ratios are omega r, omega m, omega lambda, plus omega curvature. In other words, the omegas are the fraction of h squared today contained in each one of these terms.
If we apply the scale factor to temporal dimensions, the exponential growth of time intervals applies to either 1, an increasing proportion of periods per present moments, or 2, an increased rate of the passage of time. The first corresponds with massless particle propagation, and the second corresponds with inertial mass and momentum. Changes in the passage of time coordinate can occur
without affecting the slope of the arrow of time, and vice versa.
So a model then, again, a model consists of a specification of these values, but you don't measure them completely. Some of them you measure, some you don't measure, but you just feed them in, grind the wheels, calculate A of t. You're juggling various things, but once you have a model that fits these two pieces of data, okay, then you have an A as a function of time, and you can read off it what A today is.
Where did you get those?
I didn't get them. Trial and error. Trial and error.
It fits the data the best.
This one is not important. Everybody knows that this is not important because you measure it directly. It's just too small to matter. Some of them, look, this one here is more or less measurable directly. Why? You can measure H is measurable, and you can measure the dark matter and the luminous matter together, and basically omega m is the ratio of this factor over here, this one to this one. So that actually is measurable with an assumption about dark matter. Yeah, including the dark matter, omega m is about 0.3. These two are the ones which are not known, but what is known, at least in theory, is that this plus this has to equal 1. This one is known, therefore this one follows. But you want to do better than that. Really what you want to do is, you really want to do better than that. You just don't want to say, well, this was 0.3, this one's not really known, nobody's ever measured the curvature, and therefore this one must be 0.7. That's not what you want to do. You want to take, this is given, this is unknown, and omega k, whatever it is, to fill up the difference. Okay. You with me?
Just as three-dimensional time can be substituted into the Friedmann equation and used with the scale factor instead of space, it can also be substituted into inflation theory and used with the inflaton scalar field.
Inflation, if you like, gives the initial conditions for the Big Bang. The Big Bang by itself is that initial singularity, which we don't understand. The Big Bang has certain assumptions in it. It's based on what is called the Cosmological Principle. Why the universe was as it is, so flat. It's spatially incredibly flat, homogeneous and isotropic. And once you've got something that's expanding out, then you can begin to work out what the temperature is of the universe, how rapidly the universe should expand, what it should look like today. So there are these issues which the Big Bang has associated with it that need explaining. Alan Guth from MIT, and then Soviet physicists like Alexei Starobinsky and Andrei Linde came up with these ideas to provide you, if you like, with the initial preceding dynamics which would then feed into what we now call the Big Bang. And that was called inflation. And inflation corresponds to a period where the universe actually accelerates. The size of the universe actually grows exponentially quickly. This occurred for about 10 to the minus 30 seconds. And so you have an explanation of how you can go from a universe which is on huge scales from a region which was much smaller. But where did this inflaton field come from? Where did this scalar field come from? It's got to from some fundamental theory.
Now that's not enough. We not only have to assume in order to make the model work, so we've already had to make one assumption, the Big Bang assumption, an unproven assumption. Now we've had to make a second assumption, that there's this inflation. Inflation caused the expansion of the universe to accelerate at this rate of doubling in size, you remember, once every billionth of a second. Now we have to assume this third thing, that this inflation is unstable. It has to be able to decay. And when it decays, it should decay into the matter and radiation we know. But there's at least one other major amendment we have to make to the theory. We not only have to amend something about its past, we have to amend something about its present and future. And that is this a new thing, which we've called, which is often known as dark energy. Now, this dark energy has to be put in by hand into your model in order to make it fit the data. It's only required you're putting it in by hand in order to fit the data. So, and since they're not tightly related to one another, the theory is beginning to become more of a patchwork quilt rather than a single coherent idea that we began with. So we began with a theory which we thought was simple. We end up with a theory which actually isn't that simple. It's kind of this patchwork of ideas. The ideas don't fit together naturally. Each one has to be put in and put in just so. We don't know that the Big Bang is the beginning. That was always a hypothesis. That was never, we don't know that's true from general relativity. We don't know that it's true from our understanding of quantum gravity.
Therefore, the scale factor does not necessarily apply to space. Cosmology, based on the expansion of the universe, may not necessarily be true. We may live in a universe where electromagnetic radiation redshifts, stretching out to a maximum wavelength, then breaks down after 13.8 billion light-years. The breakdown of electromagnetic radiation does not violate the conservation of energy when quantum fluctuations are taken into account.
In the infinite momentum frame, the motion of a relativistic system, when it's boosted up to enormously large momentum, behaves completely non-relativistically with respect to the motion in the plane perpendicular to the boost.
Since particles with zero rest mass can operate in an infinite momentum frame of reference, we will associate the infinite momentum frame with the period of time present time plane. Since vacuum fluctuations are suppressed in the infinite momentum frame, we will associate vacuum fluctuations with the passage of time present time plane. Quantum fluctuations relative to some inertial frame have various rates of the passage of time that decrease over an extended period of time. Relative to the infinite momentum frame, the rate of the passage of time is zero, and the periods of time and present moments correspond with the history of the universe.
Well, it turns out that empty space can weigh something. That if you actually use quantum mechanics and relativity, empty space is a boiling, bubbling brew of elementary particles, and maybe empty space can have energy. You can get rid of all the particles and the radiation, and it still weighs something.
Using this three-dimensional time model, quantum fluctuations have time reversal symmetry along the passage of time present time plane. The compactification of these fluctuations within this plane determine energy levels where pair production and annihilation have time reversal symmetry. Since the periods of time coordinate is zero in this frame, there is no arrow of time. By treating this energy state of temporal indistinguishability as a Bose-Einstein condensate, the minimal oscillation can also be treated as pseudo-Nambu-Goldstone bosons.
In the context of relativistic quantum field theory, these soft modes represent massless quantum, or so-called Nambu-Goldstone bosons. Superfluidity is the flow mediated by the soft modes, or Nambu-Goldstone bosons. And the effective theory of superfluidity can be built around that idea. So in particle physics, we have massless quanta. In fluid mechanics, we have superfluidity. They're really the same thing.
However, quantum field theory makes predictions about zero-point energy that disagree with observations concerning the vacuum energy density of outer space.
But the problem is when we try and figure out how much it should weigh, the answer we get is 120 orders of magnitude bigger than the number that actually happened. It's the worst prediction in all of physics. And the question is, will we ever understand that? Why is the energy of empty space both non-zero and so small?
We can account for the apparent vacuum catastrophe in the similar way that we were able to account for cosmological redshift using three-dimensional time.
We can argue that the vacuum energy density predicted by quantum field theory is too big because a variable rate of the passage of time is not taken into consideration. We can associate a higher rate of the passage of time with the lower vacuum energy density of intergalactic space. Though a higher rate of the passage of time is usually associated with a high temperature, the low thermal conductivity and low energy density of outer space can have a significantly higher rate of the passage of time without a relatively high temperature. This high rate of the passage of time can be associated with superconductivity.
In most cases, liquid helium is required as a cold bath to produce superconductivity. First, we want to cool the sample of tin wire. The liquid helium has been cooled below the transition temperature of tin at 1.6 degrees Kelvin. As you can see, the resistance has dropped to zero within the limits of accuracy of this instrument. Superconductivity is a state of zero electrical resistance, or, to put it the other way around, of infinite conductivity.
If we scale down the zero-point energy of quantum field theory by changing the rate of the passage of time to match that of the observed vacuum energy density, the difference between zero-point energy and the vacuum energy density becomes a function of the passage of time. For simplicity, we could write the following. Setting t double prime equal to 1 for simplicity, t prime becomes 107 orders of magnitude greater, indicating a significant difference in the rate of the passage of time between the zero-point energy and vacuum energy density. We can view t double prime over t prime as an acceleration term. If we substitute this acceleration term times the zero-point energy for lambda, we get an alternative explanation for the apparent acceleration of the expanding universe.
Paper after paper after paper has been appearing on the archives from theorists trying to explain the physics of what's going on. We were counting it is averaging roughly 2 or 3 papers every week for the past 10 years. None of them, as far as I know, would say they know what the answer is. They would say, no, they're just opening up possibilities, and they're turning back to us, the experimentalists. I would say that there's some of the theories that are much more fun to think about, and it would be great if it turned out the universe worked that way. Personally, I think it would be wonderful if it turned out that it was one of the extra dimension theories. I think that would be a really fun one if it turned out that really, what's going on is that gravity is leaking out into some other dimension, and we're not, which we're not ordinarily aware of, except we've now discovered it because of the acceleration.
Rather than accelerating, the universal scale for the different rates of the passage of time is inversely proportional to the history of the universe. The difference in rate of the passage of time between the zero-point energy and the vacuum energy density corresponds with the age of the universe. A temporal definition for mass, an inversely proportional relationship between temporal coordinates, can account for the cosmological redshift of light. Different rates of the passage of time between zero-point energy and the vacuum energy density can be used to explain away the vacuum catastrophe. Using an inversely proportional relationship between the period of time coordinate and the present time coordinate, independent any relationship with the passage of time coordinate, can be used as a solution for divergences.
Here we have these Feynman diagrams which give rise to quadratic divergences in the mass of a boson. Even if the mass of the boson was initially 0, in other words, the bare mass, these diagrams would create huge masses for the bosons. That's a problem. That's a problem for all the reasons I said. We'd like to get rid of that problem. We would like to create a theory in which bosons don't get this huge amount of mass from renormalization or from whatever we want to call it.
Our standard model gives us a detailed and battle-tested picture of what ordinary matter is, based on 2 kinds of fundamental building blocks that technically are called fermions and bosons. In this plot, as you go to the right, you're going towards shorter and shorter distances where the unification of forces will be revealed if it occurs, and you can see that they almost but not quite meet. So, to quote Homer Simpson, "No!" Supersymmetry, when it's implemented in equations, requires the existence of new particles.
It's a symmetry which relates fermions to bosons in such a way that every boson has its fermionic partner, its fermionic superpartner. They come in superpartner pairs.
Supersymmetry connects all the known particles with particles that are much heavier And this is the same picture, but with the supersymmetric particles, the partners, put in.
These cousin particles have never been observed, which is a good reason to be skeptical of the idea of supersymmetry.
These new particles have not been seen yet.
Those superpartners have never been discovered in the laboratory. Not one of them, not a single one of them. The implication is these particles must be quite massive. How massive? Basically at the edge of detectability, beyond the edge of detectability. That sounds very far-fetched that we just, by accident, all the particles, all the partners happen to be too heavy to be seen. And, you know, that really sounds like really, you know,
If you have a spin-a-half superpartner, you put in ENO at the end. If it's a spin-zero superpartner of a spin-a-half particle, you put an S at the beginning, S for scalar. And so there are electrons and selectrons, positrons and suppositrons, neutrinos and sneutrinos, and so on.
If for every boson we had a fermion with exactly the same mass and the same properties in every other respect, we could imagine, or we could conceive, that the theory might exactly cancel out the vacuum energy. So we know that, in fact, in nature, there is not this reflection of boson into fermion. If we had a theory which was sufficiently symmetric between bosons and fermions, we would at least have a chance of canceling out all this vacuum energy. So the question is there a mathematical framework that contains these kind of symmetries between fermions and bosons, which also can explain the fact that they're not exactly equal in mass in a natural way?
Unless we are using a specific rate of the passage of time to generate a mass term, we can use massless quanta to avoid changes in the rate of the passage of time. Instead of affecting the passage of time coordinate and having divergences towards infinite inertia, the infinite contributions of possible interactions can be scattered along the present moment coordinate. The spatial coordinate and the period of time coordinate are proportional. As the distance gets smaller, the periods of time get smaller as well. However, the present time coordinate gets larger such that at the limit, when the period of time interval is infinitesimally small, the present time interval is infinitely big. The present time coordinate can diverge, normalizing physical phenomena at very short distances or very high energies without generating unwanted infinities. In this case, the relationship between coordinates is inversely proportional. As the present time coordinate diverges to infinity, the period of time coordinate converges to zero. However, in terms of momentum, the relationship between periods of time and present moments, expressed through t squared, still equals 1. This allows the momentum to remain unchanged.
Now, supposing for some reason your theory was concocted in such a way that even after all this renormalization takes place, even after all the worst-looking Feynman diagrams you can imagine, that if there was enough symmetry and if every stage that symmetry was correctly preserved in detail, the cancellation of the self-energies of the bosons might also be exact.
A one-loop diagram of virtual particle pair creation and annihilation can be viewed as a time slice through a three-dimensional time loop. What makes this a time loop is the cross-conjugate relationships between forward and reverse emissions and absorptions from the vacuum. In a way, we are looking at a diagonal cross-section of a conventional Feynman diagram of virtual particle pair production and annihilation, but with the emphasis on time direction and charge. If we apply three-dimensional time to time-reverse symmetry, examining particle pair production and annihilation, we get a unique interpretation of the relationship between charge and spin. Pair production consists of particle-antiparticle pairs. A forward-time particle could pair with a reverse-time antiparticle and or vice versa. Charge could be defined as the product of the direction of spin and the direction in time. There could be 4 primary charges: positive charge forward, spin with direction of momentum; positive charge reversed, spin against direction of momentum; negative charge forward, spin with direction of momentum; and negative charge reversed, spin against direction of momentum. Examining the conjugate pairs and cross-conjugate pairs, we see equivalences. These 4 charges can be set around the complex unit circle, whereby positive forward and negative forward are complex conjugates on the positive real number side, and negative reverse and positive reverse are complex conjugates on the negative real number side. Though we can usually assume that positive forward and minus reverse, or minus forward and positive reverse, have a time-reverse symmetry, broken symmetries between positive forward and minus reverse, or minus forward and positive reverse, can be used to generate partial charges, where partial charge corresponds to variations in phase. In this case, though 4 possible spin directions can be derived, time-reverse symmetry between positive forward and minus reverse, or minus forward and positive reverse, reduce spin to only 2 directions: left-handed spin and right-handed spin. Using these relations, other spin quotients can be derived that are consistent with the Pauli matrices and block sphere.
What about fractional charge? How would fractional charge work? Assuming when a Fermi particle pops into existence, such as an electron-positron pair, it comes into existence with a slight time reversal asymmetry such that the electron and positron together act as a quasi-boson with a slight perturbation.
You plunk a quark down in empty space, and it starts to have an effect on the vacuum. In quantum mechanics, what we call empty space becomes the vacuum, and the vacuum is a very complex medium, not empty at all, contains virtual particles, and the essence of asymptotic freedom, which emerges from the calculation, is that if you plunk down a charge, its effect on the medium is to produce more charge. The charge builds up. That property of asymptotic freedom is a calculable property of the fundamental theory of QCD. It involves calculating the action of what we call empty space, the virtual particles, in reacting to charge and addressing charge. How the effective charge, the ability of particles to radiate, gets smaller and smaller as the amount of energy and momentum that is conveyed in the radiation gets larger and larger. One can start to trace out the energy momentum dependence of the effective charge, the probability of radiation, as a function of how violent a disturbance in the energy momentum flow that radiation makes.
Let this slight perturbation have a resultant charge, which can be polarized by either the electron or positron. However, the polarity and potential of this charge is uncertain, allowing slight offsets between positive and negative charges. From this, partial or fractional charges can be derived.
All of you know that electrons in a Fermi gas have a density of states which is independent of energy, but if you put on a magnetic field, that density of states breaks up into a set of discrete Landau levels. There was no energy gap in the system if you ignore electron-electron interactions. As soon as the interactions are turned on, a gap opens, and there are charged quasiparticles which have fractional charge. We know a fair bit about the charge of these quasiparticles. We don't know so much about the fractional statistics that they are supposed to exhibit. Many other states were found that were not so readily understood. You can see from this picture that there's a whole family of phenomena occurring that seem to emanate from the half-filling point. The half-filling point not itself showing a fractional quantum Hall effect. The concept of composite fermions was developed, a strongly correlated electron system in the lowest Landau level with the electrons all interacting with one another. The composite fermions are experiencing a magnetic field which is not just the external field, but as I say, it's corrected by all the flux quanta attached to all the other electrons. One can understand that picture of all those other fractional quantum Hall states in a very intuitive way. Instead of thinking of these as fractional states, you can now think of them as integer quantum Hall states, but not of electrons, instead of these things called composite fermions. And you might guess that this point here, this special point, which is the half filling, is somehow a Fermi sea, a Fermi liquid of composite fermions. Now, this is quite remarkable because, after all, you're in a lowest Landau level, which without interactions is absolutely free of any dispersion. And then all of a sudden, by turning on these interactions at half filling, it reconstructs itself in some way into something like a Fermi liquid.
The other famous feature of confinement that was thought to be very paradoxical in the early days was the fact that quarks have fractional charge. Here we have a modified U1 because the symmetry of the state with the condensate is not the original color symmetry or the original electromagnetism. The one that survives and gives a massless vector boson is a combination of the two, just as in the standard model, the emergent photon is a combination of what was originally the hypercharged boson and one of the weak isospin bosons. The original photon was described by this charge matrix. If we consider a gluon, which in color space acts with the same matrix, then acting with these two on a Kronecker delta function, the massless vector boson, which we can get by taking a combination of those two, is easily identified as this one. In fact, even though confinement has been implemented by this simple symmetry-breaking superconductivity mechanism, we find that fractional charge is gone. If we measure fractional charge as we should, according to what the photon thinks is the charge, we find that all the particles have integral charge.
Time reversal asymmetry can also be applied to baryogenesis, accounting for the initial asymmetry between baryons and antibaryons, matter and antimatter.
We think at the beginning of the universe, in the Big Bang, we had equal amounts of matter and antimatter being created. And yet, if we look at the universe around us today, we don't have equal amounts of matter and antimatter, we just have matter. And we know this because if matter and antimatter meet, they annihilate, they explode and release loads and loads of energy. And this quite clearly doesn't happen around us. Now, in order to go from a universe which consists of half antimatter and half matter to a universe that consists all of matter, then something really big and fundamental must have happened. And one condition for this to have happened is for an effect called CP violation to come into play. Now, CP violation is nothing more than a difference in the behavior of matter and antimatter. And quite clearly, if we have half matter and antimatter to start with, and we now have matter today, they must behave differently in order to reach that state. We don't really understand this effect, but we want to understand it in particle physics. It's a very important unanswered question in physics and particle physics and astrophysics all over the place.
If we use the standard figures, where for every matter particle there's roughly 1 billion photons, this suggests that the ratio between matter and antimatter is slanted towards matter by about 1 part per billion. Though slight, the basic existence equations can account for this difference. If we let A represent matter and B represent antimatter, the ratio is small, but A asterisk minus A is slightly larger than B minus B asterisk. Where A and B correspond with some present moment, A asterisk minus A is slightly into the future and B minus B asterisk is slightly into the past. It can be argued that the asymmetry between baryons and antibaryons is superficial. Forward time baryons are symmetrical with reverse time antibaryons, with the exception that forward time baryons are slightly into the future relative to reverse time antibaryons, which are slightly into the past relative to the forward time baryons. If we allow quantum spin to be a property of three-dimensional time, then the asymmetry can be reduced to an issue of chirality and helicity. For instance, in weak interactions, fermions appear to have a preference for spin away from the direction of motion. This would allow us to cross-conjugate forward time baryons with left-handed spin and reverse-time antibaryons with right-handed spin. But then, there was the Wu experiment, and then two unusual decays were uncovered for charged, strange mesons. In 1956, physicist Chen-Xiang Wu conducted an experiment on behalf of physicists Tsung-Dao Li and Chen-Ning Yang to wrest the relationship of parity symmetry with physical law. Radioactive cobalt-60 was cooled by liquid helium to temperatures near absolute zero and aligned with a uniform magnetic field. The thermal vibrations of cobalt-60 were reduced enough to study its beta decay process nearly one emission at a time. Wu found that when the cobalt-60 nuclei spins were polarized with the uniform magnetic field, significantly more electrons radiated in the opposite direction with opposite spin. In other words, there were significantly more electrons with left-handed spin than electrons with right-handed spin.
The thing that's interesting is that if you measure the spin, electrons are spinning as they come out. If you measure the spin, you find out that they're spinning to the left. That is a definite significance, that the electron, when it comes out of the disintegration, is turning this way. So all we're saying is that the right and left symmetry law is not valid. But I have to mention that conservation of parity, because you may have read in the papers that the law of conservation of parity has been proved wrong. It should have been written, because it's much easier to understand. The principle that you can't distinguish right and left has been proved wrong.
The Wu experiment shows us that the forward-time Fermi particles are able to condensate, whereas the reverse-time anti-Fermi particles are radiated away. Though this has the appearance that weak interactions have a preference for reverse-time anti-Fermi particles, the forward-time Fermi particles are able to condense first. For a slight moment, together as cross-conjugates, the forward-time Fermi particles and the reverse-time anti-Fermi particles can act like quasi-bosons. These quasi-bosons can intermediate quasi-weak interactions. The reverse-time anti-Fermi particles radiate away, appearing as electrons with left-handed spin, and the forward-time Fermi particles do not radiate away and are bound. Right-handed fermions would appear less prevalent, being bound in matter, and left-handed fermions would appear more prevalent in the form of radiation. This suggests that matter and antimatter are viewed incorrectly. We can treat the negative energy aspect of the Dirac equations as a negative time loop, treating it as a negative three-dimensional time scalar. If we plot the maximal and minimal values for t prime and t squared into three-dimensional coordinates, using t sub 1, t sub 2, t sub 3, where t prime is t sub 3 and t squared is t sub 1 times t sub 2, we quickly see that the time wave can be expressed three-dimensionally, in part using the Pauli matrices. When the time loop is expressed in the language of quantum mechanics, it satisfies the antimatter components of the Dirac equation.
There's only 3 Pauli matrices, sigma x, sigma y, and sigma z, and we need 4 matrices that have those relationships. Here's the trick. The Pauli sigma z trick is 1 and minus 1, so here we're going to have I and minus I. That gives us the extra degree of freedom, so we have 4 Dirac matrices instead of the 3 Paulis. So that says the eigenvalue for the energy for this one's mc squared, minus mc squared, minus mc squared. So you can see that the particle solution split into 2 kind of particles, one particle with positive energy, one particle with negative energy. Now, the negative energy is troublesome. We have 2 kinds of solutions in terms of the energy eigenvalues. Here is one pair of solutions, and here's the other pair.
The antimatter aspect of the Dirac equations may have been misinterpreted. The convention is to assume that matter is composed of particles distinctly different from antimatter, which is supposed to be composed of antiparticles. The hidden assumption of one time dimension locks in this interpretation of the Dirac equations. If we assume that matter consists of both particles and antiparticles cycling in and out of phase on opposite sides of a time loop, such as with an electron orbital around a hydrogen nucleus, the issue of missing antimatter disappears, and a complex relationship between time, energy, and mass appears. We could argue that matter is composed of both particles and antiparticles, but moving in opposite directions of time. Matter would be the right or stable configuration of particles to antiparticles, whereas radiation would be the wrong or unstable configuration of particles to antiparticles. Applying this to the excess baryon asymmetry equation, we could associate the excess baryons with the right configurations and the cosmic microwave background photons with the wrong configurations. This can be extended to the CKM matrix and the measurement of sin 2 beta, time-dependent parameter of CP violation in B meson decays.
For three families, the mismatch between the up quarks and down quarks means that the weak charge currents involve these 3x3 unitary matrices. The hadronic part is the CKM matrix. The relevant elements comes from beta decay and kaon decays and heavy bottom quark decays and charm decays, and eta represents the CP violation. There's two aspects to unitarity. The first aspect is the diagonal elements must be 1. The other aspect is that V dagger V 3, 1 should be 0. This is known as the Unitarity Triangle. Now, why is it a triangle? Well, these are complex numbers, and any complex number can be represented as a vector in a two-dimensional vector space. This is a vector, and that's a vector, and the last one's a vector, and so they should add up to 0. They should form a triangle. Turns out if there were no CP violation, then all of these would be along the real axis, and so somehow the area of the triangle is measuring the amount of CP violation. One expects to have in the rho eta plane, by dividing that out, one of the elements just is at 0, 1. That's this vertex. These angles in this parametrization are called alpha, gamma, and beta. Vector is rho plus I eta, and this is 1 minus rho minus I eta.
This framework allows a re-examination of the rho eta plane used for plotting the unitary triangle, but in terms of temporal coordinates. T1 would equal a length of A slightly shifted forward into the future, and T1 prime would be the length of B slightly shifted backwards in time. Remember, we had designated this as period. With this dimension of time corresponds here to both A and B having a change in their passage of time. If we examine the mathematics for measuring decay rate, the decay rate can be associated with the periods of time component, and the mean lifetime can be associated with the passage of time component. Since the base expression for mass equals the absolute value of t prime times t squared, there are two possible observations. First, we are dealing with decay rates of time, so we can set the passage of time as the vertical component for both b minus b asterisk and a asterisk minus a. This forces the period of time coordinate to be different between b minus b asterisk and a asterisk minus a, resulting in a time reversal asymmetry. The longer the lifetime of a particle, the less uncertainty there is in the mass energy. The shorter the lifetime of a particle, the more uncertainty there is in the mass energy. On the other hand, we are using a model compatible with massless particles, so we can set the present time as the vertical component for both b minus b asterisk and a asterisk minus a instead. In this case, the period of time coordinate is different between b minus b asterisk and a asterisk minus a, resulting in a different type of time reversal asymmetry. In the first case, there is a mass invariance, whereas in the second case, there isn't. In the second case, b minus b asterisk and a asterisk minus a can both have the same passage of time, that is, the same mass, though there is a break in simultaneity. Re-examining CPT symmetry, time reversal asymmetry is equivalent to a charge parity asymmetry. If we take both types of time reversal asymmetry, where the passage of time coordinate values are inversely proportional to their corresponding linear time values, then the uncertainties between b minus b asterisk and a asterisk minus a smooth out, and a relative to b equals b relative to a, even though a relative to a does not equal b relative to b. This isn't a contradiction, this is an identity crisis, where the Pauli exclusion principle and the inclusion principle correspond with quantum entanglement. If a equals b, then a over b equals 1, and the identity constant is 1, meaning there is only one particle, physical state, field, etc., depending on the application. If a is greater than b, then a over b is greater than 1, and there are at least two particles, states, fields, etc. When a over b is 1, this corresponds with the inclusion principle. When a over b is greater than 1, this corresponds with the exclusion principle. In quantum mechanics, it is impossible to know both a particle's momentum and position simultaneously within an accuracy greater than h bar. This is known as Heisenberg's uncertainty principle. Using three-dimensional time, we can apply both the inclusion principle and the exclusion principle simultaneously and account for the uncertainty principle, allowing for the basic existence equations to apply generally to quantum mechanics. We can argue that charge parity asymmetry and time reversal asymmetry are indicators that CPT symmetry is incomplete as a fundamental symmetry of physical law. The basic existence equations can account for mass invariance using 3 dimensions of time. So how do we account for an invariance or break in this symmetry? M violation. What is M violation? Since charge parity and time reverse symmetry are equivalent, charge parity and time reverse symmetry together in this 3-dimensional time model is equivalent to mass symmetry. M violation becomes central to the quantization of gravity. Using the classical gravitation equation, Kepler's second law, and substituting a temporal radius for r, we get the following. If we assume Einstein's equivalence principle, a variance in acceleration or mass would indicate an inequality, and t squared could not equal 1. However, if the two masses are significantly different, then t squared can have different values relative to different rates of the passage of time in correspondence with each mass without violating Einstein's equivalence principle. If two particles are in the same state at the same time, and it is not possible for them to change state in order to avoid violating the exclusion principle, the identity of each separate particle can become indistinguishable, resulting in just one particle. One of the masses is converted to a relative time and conserved through a change in the rate of the passage of time. The gradient of change in the rate of the passage of time of the massive object is the gravitational field of that object. Since we are dealing with various rates of the passage of time, differing mass distributions of point particle masses, the difference in the passage of time between various masses in different locations will displace the center of mass towards equilibrium through uniform invariant motion, inversely proportional to the distance and proportional to the period of time the motion takes place in. We know this simply as gravity. These four potential relations have a complex conjugate type of relationship where, relative to the lighter mass object, we get the following frames of reference, and relative to the heavier mass object, we get these frames of reference. From here, we can derive two equations for acceleration, one relative to the falling object, the other relative to the massive body. What we can see is that these two equations are conjugates. Therefore, both masses are experiencing the same acceleration, though not in the same way. Looking at the passage of time component in the temporal definition for mass, the relationship between temperature, mass, and so on are byproducts of viewing the universe through an inertial frame of reference. Referring back to the sin 2b measurement, this double angle gives us a value of approximately 0.69. This is almost the value for the sine of 45 degrees, suggesting that the time-dependent parameter of CP violation in B meson, as predicted by the CKM model, may correspond with a phase transition. In our model, this phase transition could be between cross-conjugate pairs or between forward-time particles and reverse-time antiparticles. The transformations between left-handed to right-handed or right-handed to left-handed fermions, which is associated with generating a mass associated with weak interactions and the neutrino seesaw mechanism, is better understood through cross-conjugation and cross-symmetry. We can speculate that the values associated with dark energy correspond with phase transitions of quantum fluctuations over periods of time that correspond with the history of the universe. This suggests that there may be a relationship between the time-dependent parameter of CP violation in B meson decays predicted by the CKM matrix and the values associated with the lambda CDM model of the universe. These may correspond with the same phase transition, but reflected on severely distinct timescales. According to quantum vacuum zero-point energy, the lowest possible energy a quantum mechanical system can have is the ground state, which too undergoes quantum fluctuations. Symmetries between beta decay-like and reversed anti-beta decay-like phenomena could oscillate in a time loop as a temporal superposition of a hydrogen atom-like structure. These diagonal symmetries appeared to take into account charge parity violation. A forward and reverse time loop model resembles aspects of Heisenberg's uncertainty principle, incorporating a new principle into quantum entanglement, the inclusion principle. The inclusion principle and the Pauli exclusion principle work together to account for quantum entanglement, but in a new way. The basic existence equations and three-dimensional time can be applied to quantum entanglement, creating a dichotomy between the Pauli exclusion principle and a new concept, the inclusion principle.
It's a little technical, but very paradoxical, is that we've had a rule back for atoms that no two electrons can occupy the same state. It's called the exclusion principle. And we thought we understood that that was necessary according to quantum mechanics and relativity, it has to be. And with the quarks, we find the exact opposite rule. Two particles tend to occupy the same state. The exact opposite. It seems to be contradictory with principles. We don't find experimentally any such particles. Now everybody's looking for them. But it looks as if they exist at all, they have to be extremely heavy. Then the problem is, very good, if they're extremely heavy, how, compared to a proton, say, how is it when you put three of them together, you get a light object that's not heavy, like the proton? There are technical ways of arranging it, but they're always complicated. The situation is, as it always is when we're near the answer, it looks much simpler than it has any right to be. And the question is, what way do we have to think about it so that we understand its simplicity? That's where we stand now.
Starting from a quark soup of quantum fluctuations, there is some probability for structures to form with varying degrees of stability. For instance, some quark configurations, such as mesons, are not very stable, whereas other configurations, like neutrons or protons, are more stable. Using cross-symmetry and cross-conjugation, we can create a neutron from quark fluctuations. From this, we can transform a neutron into a more stable proton. Because protons carry charge, a virtual electron-positron pair has a probability to polarize with the proton. The reversible process of electron capture, or inverse beta decay, could spontaneously form an oscillating temporal loop of beta decay, anti-beta decay, beta decay, and so on, which can account for both quantum electrodynamics and quantum chromodynamics. What this suggests is that matter is composed of both particles and antiparticles. We have already examined how 3 dimensions of time and the basic existence equations can account for how this could be possible. The equation used in baryogenesis to account for the asymmetry between matter and antimatter can be reinterpreted. The numerator corresponds with an excess of baryons over antibaryons, and the denominator corresponds with the CMB radiation left over from baryon-antibaryon annihilation. Therefore, there is no missing antimatter or excess of baryons. Rather, baryon and antibaryon structures have stable and unstable configurations such that an emergent universe can arise from quantum fluctuations without a Big Bang. The asymmetry between particles and antiparticles is both a driving mechanism and cause for the stability of matter. This model can be used to account for physical phenomena associated with nickel-titanium and negative Kelvin temperature.
This giant complex of buildings overlooking San Francisco Bay is the Lawrence Laboratory at Berkeley. Some of the world's most advanced research in theoretical and practical physics is being done here. For some years now, a small group of scientists attached to the laboratories have been investigating this, a curious metal called nitinol. It has certain anomalous properties not yet fully understood or explained. It's caused considerable interest, it has generated some controversy, it may have profound consequences.
Nitinol had apparently unique properties. The head of the laboratories was Nobel Prize-winning physicist Professor Edwin Macmillan.
Well, this is a piece of nitinol which was made in the shape of a coil spring, and the property of nitinol is that it when it's hot and wants to get back to the shape it was when it was made. When it's cold, it's quite relaxed and will take any shape. In the cool state, it's relaxed and floppy. In the heated state, it remembers its former state. That's why you say it has a memory. So if you make the thing, if you make this piece of wire so it's straight when you made it, then when it's hot, it wants to straighten out. When it's cold, it's just as floppy as a wet noodle. You know, if you take one of these things and put it in hot, cold water and feel it in your hand, it's like a wet noodle when it's cold. When it's hot, it straightens out very suddenly. It's quite strong stuff.
The actual phenomenon itself is not yet fully understood. An engineer at the laboratories, Ridgway Banks, set out to build an engine to harness this. In a small workshop across from his office, he designed and built a wheel with nitinol loops hanging from the spokes. He calculated that if he filled a container with cold water and another with hot water, the loops of nitinol, moving from one bath to the other, would bend, then spring back, and that the sudden spring of the nitinol in the hot water would drive the wheel around, thus becoming the world's first solid-state heat engine. He was right.
Science blogs are buzzing over a new experiment, one that leaves most laymen scratching their heads. The study in the journal Science claims to have created an atomic gas with negative absolute temperature, meaning a negative number on the Kelvin scale. Hold on, how does something get colder than the coldest possible state? If you're like most high school science students, you were probably taught that absolute temperature is the measure of how much atoms vibrate. As you get colder and colder, they vibrate less and less until they come to a standstill at absolute zero. But science writers trying to explain the latest experiment say that's not quite the whole story. A more accurate description of temperature would represent a loop. Anything beyond absolute zero or infinite temperature would be in the negative. Hopefully that gets the point across. Negative doesn't mean below zero, it means the opposite of positive. It's basically a different state of matter, a kind of hot-cold.
This suggests a time reversal phase transition associated with certain temperatures that correspond with the forward time particle and reverse time antiparticle interrelationships with certain states of matter. According to this model, hydrogen isotopes such as deuterium could be viewed as forward time beta decay and reverse time anti-beta decay bound in a time loop. Rather than annihilation, a temporal loop is formed that oscillates relative to the temporal asymmetry between phases. This could be used to explain the stability of hydrogen as opposed to antihydrogen.
So hydrogen, for example, consists of a proton and an electron. Now, if you took an antiproton
the antiparticle of a proton, and a positron, the antiparticle of an electron, and put them together, you could make anti-hydrogen.
They managed to combine the positron and an antiproton together, and they found anti-hydrogen. But they couldn't stabilize it, because as soon as a particle and its antiparticle meet, they annihilate.
And so the new development is that they've actually found a way not only of making anti-hydrogen, but actually trapping it with a strong magnet. You can actually create a magnet which holds these particles.
They've trapped 38 of them for about 1/6 of a second. Right, so it doesn't sound great. To be able to trap them, and that many of them, for 1/6 of a second is a real achievement. And so they're using combinations of very strong magnetic fields and electric fields, because to stop the particles, of course, they mustn't hit any matter, because when matter and antimatter hit, they annihilate.
Cold antihydrogen, of course, we're meaning temperatures which are not at 4 Kelvin, which is where we've typically worked. We actually have some of our plasmas down at 1 Kelvin. Why is, 4 Kelvin down to 1 Kelvin, big deal? It's only a factor of 4. Well, it actually is a big deal because it happens in the exponent. Okay, in a Boltzmann distribution. So that means that we get a large, many more antiprotons that are cold. Our basic goal is to make a precise comparison of antihydrogen and hydrogen structure using laser spectroscopy. But the point will be, if we compare a Rydberg and an anti-Rydberg, for example, it will depend on all these charge and mass ratios of particles and antiparticles, which by the CPT theorem should be the same. Okay, and so if the Rydbergs are different, we'll have some sensitivity to a lot of different quantities.
The forward time particle and reverse time antiparticle configurations would be stable in hydrogen, and the forward time particle and reverse time antiparticle configurations in antihydrogen would be unstable. Returning to the concept of mass, our temporal definition of mass must maintain consistency with the Higgs mechanism, which is used to explain the mass of gauge bosons.
The mechanism is built upon two things. Scalar fields, this is these objects which are here, and the gauge fields. One had to find gauge fields that have a mass. Nobody knew how to do it, essentially. And the interest of that is because these fields are those which give rise to short-range interaction. That means interaction which act at very small scale inside the nuclei of an atom and things like that. So we invented a scalar field, which is this object with phi. We decomposed one of these fields. This field here is what's called a complex field. It means it's a collection of two fields, which can be called phi 1 and phi 2. And one of these fields gives rise to a condensate that is spread out all over the universe. And it is the interactions between A mu and that condensate which gives the field. That gave rise to short-range interaction and could be generalized to give mass to all elementary particles. That is due to this condensate. To detect that condensate, you have to find this slightly leftover piece, which is essentially a particle, which is the particle which was detected at CERN. The other part of the field, that one, is just an object which disappears into that field and is necessary for the consistency of the theory. So that one disappears from the spectrum. One doesn't see it, but it's there to allow this one to sustain a mass which you would not have the possibility if that does not exist.
Many of us are terrified that the LHC will discover a Higgs particle and nothing else, because that would really give us that would just confirm the standard model in its simplest form. And what we really hope is that we'll see something that goes beyond the standard model, and the number one candidate for that is supersymmetry.
It could be that we learn at the Large Hadron Collider that our universe isn't four-dimensional, that there are more dimensions. And that would change the whole nature of space-time. and might reveal some new aspects of time. The only way we'll probably learn about the nature of time is to keep on looking for these weird and wonderful things.
Furthermore, our temporal definition of mass must also maintain consistency with the experimental data in support of a discovery of the Higgs boson.
This kind of field has two distinct kinds of quanta associated with it, one massless, one massive. Oscillating this way, we would call the Higgs boson, and it has a mass. What about oscillating this way? That's the Goldstone boson. It's massless, but there is no massless Goldstone boson in nature. So something happened to it. In the parlance of high-energy physics, the Goldstone boson got eaten by the gauge boson, resulting in giving the Higgs boson a mass.
Given that T squared corresponds to the Goldstone boson, and changes in the Higgs field in this direction corresponds with T prime, it can be argued quite easily that the Higgs field is nothing more than a scaled version of three-dimensional time, accounting for particle mass in the very same way that the relationship between T prime and T squared account for mass in temporal mechanics. However, there appears to be an additional surprise. When we examine the experimental data in support of a discovery of the Higgs boson, there appears to be a significant anomaly. By 2004, I had reconstructed key issues in theoretical physics to account for current and yet to be discovered experimental anomalies. My entire model, to a certain extent, boiled down to a single interpretation. From the very beginning, I saw that variations in the relative rate of the passage of time should correspond with particle decay and mass somehow. There was no way of avoiding making specific predictions about the Higgs boson.
Even though we don't know which theory governs the behavior of Higgs bosons, or if they even exist at all, we understand very well what the Standard Model predicts about the Higgs boson. The Higgs boson is on the left, while there are 5 other particles arranged in a column on the right. They are the most common particles into which the Higgs boson can decay. This is how we search for Higgs bosons. We pick a mass we want to study and find out how Higgs bosons of that mass are likely to decay.
With the big announcement that's going to be made on July 4th, I really doubt that they're going to come out with the big grand announcement of finding a Higgs particle and finding it in such a way that it satisfies all of the expectations. A more complex concept of the Higgs particle would be needed.
If we combine the ZZ and gamma gamma, a combined significance of 5 standard deviations.
We have an excess of one big spike here in this region here.
As a layman, I would now say
we have bagged the Higgs boson.
We have observed a new particle consistent with a Higgs boson. Huh. Which one? That remains open.
The Higgs was exhibiting identity crises between the decay channels of the Atlas detector and the CMS detector. This indicated entanglement between the Higgs phenomena in both detectors. If we assume that there's just one Higgs particle, the problem is that in the CMS detector, the lighter mass is in the gamma-gamma channel, whereas in the Atlas detector, the lighter mass is in the ZZ channel. So this would indicate that the Higgs to gamma-gamma channel has more mass than the Higgs to ZZ channel. And then it's the ZZ channel now that's more massive, and it's the gamma-gamma channel that's lighter.
How about that?
The Higgs to ZZ channel has a heavier mass here, and the Higgs to gamma-gamma has the heavier mass here. What's your opinion about that?
It could be a resonance phenomenon.
So
this is count at a certain energy.
Yeah, exactly.
Okay.
They're not showing any coupling with the leptons or the quarks.
Well, that's right, yeah. It's just going to bosons there.
So we could correspond the masses like this. The problem here is that we have one particle and 2 detectors at the same time in both instances, which is extremely peculiar and odd. So what's the alternative? And that is to go, okay, well, what we have is we just have a single Higgs particle, but there is a mass variation that's happening with its decay modes. The problem with that is then we have to explain not only why there is a significant mass difference between the gamma-gamma and the ZZ channel, but why that reverses between the detectors. It looks like we're having sort of a quantum behavior of do we have one particle or two, and it looks like it depends on how you measure it.
So the issue was actually a resonance phenomena and some sort of a correlation inside the ring where you would get correlation between what's detected here and detected there, and there's this observable some sort of phase phenomena between the two, so that there could be new phenomena of the protons circulating in there, and that could have properties that we don't know.
What the Higgs paradox is it appears that we have either one particle in two detectors at the same time, or we're having two particles and in some way they're entangled in some new form of quantum behavior. So for there to be entanglement between the two detectors actually isn't that peculiar at all then, is it?
No,
it's unexpected, but it's not peculiar.
It could, each proton could have a wave function inside the ring.
This wasn't really weird as far as quantum mechanics is concerned, but oddly, it demonstrated a link between quantum entanglement and identity crises. In other words, this was a direct detection of the inclusion principle. The experimental data indicated the presence of not just one Higgs field, but two.
Well, the Higgs can interact with other particles, and what's predicted is that the Higgs will interact more often, for example, with a top quark than with a deep quark, has a stronger coupling to the top quark.
Well, what have we actually measured as of July of last year? We measured these guys with pretty good detail. We made some measurement of these guys, but they weren't all that accurate. And that's where we stand. We didn't measure this, we didn't measure this, we didn't measure this, didn't measure this. I mean, these are the things as of July 2012, what we measured. Nothing that we measured showed it to be wrong, but that doesn't mean that it was right. It just means not guaranteed wrong.
The discoveries were for the Higgs boson decaying into a class of particles called bosons, which has a spin that's an integer, 0, 1, 2, 3. There's another class that have half spin, 1/2, 3/2, and so forth, and we only really look at 1/2 ones. And we've recently seen that not only do we get the same thing from what we discovered, which were the 0, 1, 2 particles, we're now seeing it in the half particles.
We know that the matter particles interact with this Higgs boson. We also know they do it differently.
So here's Atlas, here's CMS. This is data measurements. Now, what should it look like? If the Higgs boson didn't exist and everything was perfect, we would see the data along this left-hand line. If the Higgs boson existed and it was exactly as predicted, we would find the data on the right-hand line. And again, CMS and Atlas. So that kind of tells you what you should be looking at. And this is what we had talked about. But so if you have to really learn statistics, if you're going to do particle physics, you have to take this kind of data and come up with an answer from it.
You could imagine an explicit symmetry breaking, which would correspond to tilting the potential a little bit.
What we're seeing with the Higgs data between Atlas and CMS is two overlapped, explicitly broken symmetries.
My name is Dag, I work for Atlas, and I was presenting some measurements of the Higgs couplings to other particles.
So the strength of the coupling is what determines how often it decays to different things or is produced by different things.
That's right. We can see then how if this agrees with what we predict, or if there might be some new production mechanism that we haven't thought about yet. What we see is that it's within this precision we have. It looks like what we predict, even if you can maybe see a little hints of a few more jets.
I'm Stephen from the Atlas experiment, and my analysis, or my research, sorry, is on dark matter searches at the LHC. So I've been spending a lot of time in both the Beyond the Standard Model sections and the astroparticle physics sections. So I can try to provide a bit of details there. You could say, well, why do we think that dark matter has any connection? So maybe this is with the Higgs, maybe there's a connection between standard model and dark matter with the Higgs, maybe there's something else we don't know. There's a lot of theories out there which say that basically the best way to access new physics beyond the standard model is through the Higgs. There's a lot of reasons where you could say that could go for that. And for example, dark matter is one of the prime candidates where you could say that dark matter is related to mass and Higgs is related to mass, so there could be some form of extra special coupling there, so some special interaction where the only way you can produce dark matter is through the Higgs.
Searches for the Higgs boson decaying to invisible particles, where you look at the things going the other way, and that's one of the things we need a lot more data for.
So we found something new, and we're still trying to figure out what it is, what it does, what it means.
We found this thing that could be the Higgs boson. Let's pretend it's the Higgs boson. What happens is the Higgs boson will go along because of quantum mechanics. It'll turn into top quarks and antiquarks and go back to the Higgs boson. And it'll do all sorts of stuff. But the net effect is all these things, what we call quantum fluctuations, takes the observed equals theory and adds this term. So the maximum energy, if you look down here, turns out to be 10 to the 38, which is a big, monstrous number. This term here, bosons minus fermions, and the maximum energy, when you multiply those two guys together, it has to be really, really small, because this is a big monster number. So this number has to be really tiny, like 10 to the minus 38. If it isn't, then what we would observe would be huge. So the fact that we found a small mass of the Higgs boson is freaky. So there are some options. It could be that this 10 to the 38 GeV thing is wrong, or the Higgs boson has stuff inside it, like a proton does, in which case the standard model breaks. Alternatively, this boson minus fermion thing is equal to 0. And one way to do that is this theory called supersymmetry. This, however, is an absolute screaming idea that no matter what, the small mass of the Higgs boson means there must be new physics, and it's in these two terms.
We have one like this, an explicit symmetry breaking like this, an explicit symmetry like this, and what this represents is not only the inclusion principle and how it relates to quantum entanglement. These two forms of explicit symmetry breaking are actually what we'll call M violation, or a violation in mass symmetry between the two decay channels measured at ATLAS and CMS. On June 20th, 2014, I asked Seth Zenz over Twitter, what is the CMS position regarding the Higgs mass? I'm seeing twin peaks in CMS data similar to ATLAS. Is CMS acknowledging it? He responded, CMS most recent here. ZZ and gamma gamma are consistent, both values inside combined 68% contour. However, less than a month later, on June 3rd, CMS publishes a paper concerning the precise determination of the mass of the Higgs boson, and on page 11, the graph looks much different. The overlap between the ZZ and gamma gamma channels is getting more pronounced, similar to the twin peaks found in the June 15th ATLAS publication concerning measurement of the Higgs boson mass. If we compare the CMS and ATLAS data side by side, we see pronounced twin peaks in both data sets, but with a significant difference. In the CMS data, the ZZ channel is significantly more massive than the gamma gamma channel, yet in the ATLAS data, it is reversed, with the gamma gamma channel significantly more massive than the ZZ channel. As of summer 2014, the Higgs Paradox was becoming more and more apparent. Then, on September 1st, physicist Frank Close tweets, Higgs to gamma agrees with standard model. So much for Higgs to diphoton excess in ATLAS. Furthermore, Andreas Warburton tweets, Higgs to diphoton results from ATLAS has excess, but latest measurements agree well with standard model. On September 9th, ATLAS had published a paper regarding the measurement of Higgs boson production in the diphoton decay channel. On the surface, it appeared that the anomaly I was focusing in on had disappeared. However, a deeper look into the publication revealed apparent efforts to brush away the anomalous Higgs to diphoton data, though it was still showing a discrepancy. For instance, on page 27, it shows a diagram where, in order to fit the data to the expectation for the standard model, the observed and expected results indicate 68% confidence. Yet, if we look through the paper, including closely at the same diagram they reference, a higher confidence level would correspond with a higher mass, more consistent with the data from the past 2 years. For some strange reason, I decided to scroll through the auxiliary figures and tables that were not included in the official publication, and I found this, Figure 22. This clearly shows that the observed mass is significantly more towards 126 GeV than the expected value. A more honest graph would have looked something more like this. Is this why the graph was not included in the publication? On November 22nd, I sent a tweet to physicist Frank Close stating, "I read the paper and examined the auxiliary material. Not so fast." He replied, "What specific points worry you in the paper? I hope for Higgs to gamma-gamma deviation to go beyond the standard model, but zero significant data." I responded, "Notice how the twin peaks switch between CMS and Atlas?" He responded, "Hardly significant enough to claim a drama, but nor can one rule it out. Time and more data will resolve this." I initiated a similar conversation with Andreas Warburton, one of the Atlas collaborators, on the September 9th paper. He stated, "Thanks for reading our paper and auxiliary plots. Note, standard model can't predict Higgs mass." I responded, "Notice that the twin peaks switch between CMS and Atlas? This hasn't gone away as far as I can see." To which he responded with, "You began the thread with paper on Higgs to gamma-gamma standard model rate versus Atlas, but now have switched to gamma-gamma versus ZZ and CMS versus Atlas and Higgs mass." I responded, "First was drawing your attention to auxiliary plot. Second was drawing your attention to possible significance still in plot." He responded, "You appear to be mixing up two separate questions, but it is good to keep a close eye on all this. Stay tuned for future results." My conversation with Seth Zenz at CMS and Andreas Warburton with Atlas are very revealing. I don't think physicists are trying to brush aside the anomaly I keep drawing attention to. They are trying to verify the standard model Higgs, which is what the experiment was designed to do. However, CMS and Atlas both have to slant their data, so to speak, to get a 68% match with the standard model. Though I am extremely impressed with the effort and expertise put into these two experiments, I'm equally blown away that both experiments appear to be fixing the data while ignoring a potentially new discovery, something that goes beyond the standard model. Therefore, I predict that after the LHC increases the brightness of the proton beam, that the reverse twin peak data will continue to show up in their data plots. The significance of this twin peaks data, or what I've been referring to as the Higgs Paradox, is that it shows two opposite explicitly broken symmetries. This matches the concept of identity crisis. The basic existence equations can be used in two different reference frames, where one frame is more spatially oriented, corresponding with position, and the other frame is more temporally oriented, corresponding with momentum. Let's assume that the H plus state has its own Higgs field, the H minus state has its own Higgs field, and that these fields vary according to the new equivalence principle. Since the H naught is a massless Goldstone boson, we will let it intermediate between the H plus field and the H minus field. Since the H plus field mass is more associated with photons, it is slightly ahead in linear time, and since the H minus field mass is more associated with Z bosons, it is slightly behind in linear time. However, relative to a position frame of reference, since the H minus field overall bears less mass than the H plus field, the opposite is true. There is an interesting coincidence between the excess diphoton channel in the Atlas detector and a seemingly unrelated physical phenomenon. Rather than there being an inflationary period after the Big Bang, this would suggest a deflationary period, where electromagnetic radiation begins to break down 13.7 billion light years away from an emission source. However, this revised higher light theory has a major weakness. How do we get from long wavelength with low temperature, with high redshift, to light with a short wavelength or high energy photons, such as in the Primakov effect? When I first decided to go with the Primakov effect as part of my explanation for the cosmic microwave background and what happens to red-shifted light along the cosmic horizon, I didn't take into consideration very significant consequences.
It is a strange and mysterious feature of microphysics that it looks almost the same when run backwards in time. If you take an ordinary movie, say Groundhog Day, and run it backwards in time, it would look very, very strange. But if you took a movie of events in the micro world, atoms doing their thing, and ran it backwards, it would be almost impossible to tell the difference. The laws work the same, forwards and backwards in time. This funny feature of the microphysical laws is an accidental feature, a result of other profound principles. And this is work for which Kobayashi and Masukawa won the Nobel Prize. But their explanation is not complete. It leaves a big loophole. There's one possible source of asymmetry between the directions of time that their theory doesn't address. We can close the loophole by embedding the standard model in a bigger, more symmetric theory. When we do this, we find we get a remarkable new kind of particle, the axion. When you work out how axions behave in the Big Bang, you find that they're likely to supply most of the dark matter of the universe if they exist at all.
There is a chilling similarity between the strong CP problem, Peccei-Quinn symmetry, dark matter axions, and the basic existence equations applied to three-dimensional time. Strong CP problem is the mysterious fact that charge parity symmetry violations do not show up in strong interactions, though they are predicted by quantum chromodynamics.
Pseudoparticle solutions of the Yang-Mills equation. They carry some charge of some kind, quantized charge. They're called instantons because they appear in this funny time coordinate. They appear and they disappear. The more interesting thing is when you integrate the fields in this object, it carries CP. It carries CP. If it winks in and out, you've got CP violation.
The other great unnatural fact within the standard model is the smallness of the so-called theta parameter of QCD, a parameter that could have, but in fact in nature does not, lead to significant time reversal symmetry violation in the strong interaction.
You would have expected the strong interactions in the standard model to violate P and CP. There is actually an angle called theta, and the standard model does not provide a reason why theta is small.
The relationship between the inclusion principle and the exclusion principle, our treatment of CP asymmetry and the unitary triangle, and time reverse symmetry in three-dimensional time can all be used to account for the strong CP problem. What is interesting is that our model is congruent with the best known theoretical solution to the strong CP problem, Peccei-Quinn symmetry, and the scalar particle known as the axion.
Well, an axion is a particle we need to introduce. Without axions, the standard model has this kind of suspicious coincidence. An effect that could occur doesn't occur, and the axion is meant to make that something we can understand.
Peccei and Quinn found a nice explanation. They said that this angle can be made a dynamical variable. The theta is replaced by a field divided by a decay constant called the axion decay constant. The field relaxes to zero and the strong CP problem disappears. But you, as Weinberg and Wilczek pointed out, when you do that, you have a quantum of the field, an oscillation that's present in the low energy theory, and that quantum is called the axion. So it's a particle associated with the field phi.
It's sort of like a photon, it's the quantum of a field, but Unlike photons, axions have a mass. It might be a very, very small mass. It's electrically neutral, has very, very feeble interactions of other kinds. The microscopic basic interactions have this property called time reversal invariance. Why in the world should there be this symmetry of the microscopic laws, that you have this accidental consequence that the laws are almost the same forwards and backwards in time?
Reading Frank Wilczek's 1977 paper, Problem of Strong P and T Invariance in the Presence of Instantons, he states, the requirements that parity and time be approximately conserved in the color gauge theory of strong interactions without arbitrary adjustment of parameters is analyzed. Several possibilities are identified, including a remarkable new kind of very light, long-lived pseudoscalar boson.
This theta zero I've been talking about, the initial misalignment, controls the dark matter density but has little or no effect on anything else. It doesn't affect the values of quark or lepton masses, the number, any of the structure of the standard model, except for the theta parameter. Nothing appears to depend on this variation of theta zero, except for one particular thing, the ratio of dark matter density to ordinary matter density.
Wilczek examined whether such a small quantity can emerge in a credible way from gauge theories or if the small angle theta can be made zero in some sense. At least one of the following four conditions must hold. Parity is softly broken, leading to some awkwardness in understanding the two-component neutrino. Time is softly broken, and an axion with properties to be detailed below exists. Pesce and Quinn have made the ingenious observation that we might consider a chiral symmetry. This leads to a special kind of Higgs boson, the axion. Two separate phase rotations give us two potential Nambu-Goldstone bosons, since the vacuum is not invariant under them. It will decay overwhelmingly into two photons.
It hasn't quite been tested yet, but the crucial experiments are underway. They're based on a sophisticated sort of antenna which converts the ambient axion radiation into more experimentally accessible microwave radiation by the process of A goes to photon-photon, where one of the photons is an external magnetic field.
You can detect axions by converting them to photons in a magnetic field, and the effect can be enhanced in a resonant cavity, which happens to be tuned to the axion mass. You get an enhancement. And there's an experiment. This is actually something that could detect axions today, and there's an experiment called ADMX.
What you see in blue, that is our published limits. The two bands we have here, that kind of is our goalpost. The experiment that we're putting together at University of Washington right now will bring it down a couple orders of magnitude. We'll be able to actually look, even if the axion was fractional halo densities, we could still see them. Mm-hmm. So this is a really exciting time for the ADMX experiment. We should really start being able to cut into this model space. And so that's kind of one of the reasons that I think this is a prime time for axions.
So it has to be, say, lighter than 10 to the minus 3 eV. But also it has to be heavier than 10 to the minus 6 eV.
So there's only a small window between the experimental bounds and the cosmological expectation here. And that's another way of saying that axions are almost forced to be an important component of the dark matter if they exist at all.
A quick look at the specs for the ADMX experiment shows it is designed around the theory that the axion will convert into two photons in magnetic fields with a magnetic flux density of 8 Tesla. This is chilling too, because if we read from Romeo Perrin's 1985 paper, 8 Tesla dipole magnet for the Large Hadron Collider, he states, for such a collider, bending magnetic fields in the range of 8 to 10 Tesla are envisioned. Is it possible that we are seeing some kind of axion contamination in the Higgs boson data at the LHC? I'm not the only one to ask this question. If we go back and look at the video Evolution of Time, I suggest that there is a single Goldstone boson interacting in two Higgs fields. Could this hypothesized Goldstone boson, appearing to correspond with two different Higgs eigenstates through explicitly broken symmetry, be some kind of axion?
This particle is almost a Nambu-Goldstone boson, but its parent symmetry, what's called Peche-Quinn or PQ symmetry, has a small intrinsic breaking through quantum anomalies.
Furthermore, axions appear to be the final candidate for dark matter particles. Of all the mainline theoretical explanations, axions have not yet been eliminated.
What we need is something called cold dark matter. So the particle has to be stable. It has to be sufficiently weakly interacting, let me call that collisionless, but also it has to be sufficiently cold.
And then if you work out its history during the early universe, how much axions would get produced, you get the wonderful surprise, which wasn't put into the theory, but produces a very good candidate to make the dark matter. So it has the right properties in itself, and also it's produced in the right amount to make dark matter.
Returning to our temporal blob, the spatial 4-vector spreads out homogeneously over more than one place at the same time, while the temporal 4-vector remains in the same place at more than one time. The temporal 4-vector, which acts like a billowing temporal blob, has a single spatial dimension cross-section, a point, whereas temporally it spreads out over 3 dimensions of time. Besides mass, could this temporal 4-vector be used to describe axions? And the spatial 4-vector be used to describe a homogeneous distribution of axions, such as a Bose-Einstein condensate?
There are hot axions produced by thermal processes, but there's an additional population of cold axions not produced by thermal processes, but so-called vacuum realignment. And the two populations stand in contrast to one another. So the hot axions, the typical momentum is GeV, but the cold axions, their typical momentum is the inverse of the age of the universe, which is like 10 to the minus 9. So why does this cold axion appear? It really appears because of the finite age of the universe. When the universe starts off, the axion field has no preferred value. And then during the QCD phase transition, it wants to align to 0, but it cannot dissipate, and it keeps sloshing back and forth.
The temporal model already has major overlaps with Bose-Einstein condensates through the concept of identity crisis. Though the concept of identity crisis in existics and in condensed matter physics are slightly different, we find compatibility between our temporal blob and an axion Bose-Einstein condensate. Referring to a paper titled Using Cosmology to Establish the Quantization of Gravity, written by Lawrence Krauss and Frank Wilczek, it reads, "While many aspects of general relativity have been tested, and general principles of quantum dynamics demand its quantization, measurements of polarization of the cosmic microwave background from inflation in the early universe would firmly establish the quantization of gravity. In the de Sitter limit, the inflationary epoch is characterized by a single parameter, the Hubble parameter. A contemporary gravitational wave background that was produced during the inflationary epoch will require gravitational interactions and thus will involve the gravitational constant g. The energy density in gravitational radiation after inflation ends gives a physical measurement of the strength of the background, but it varies with the length scale, A, of the expanding universe as 1/8. If we want to extract a relic from the early universe, we must compensate that factor. Inflation also, in general, predicts an almost flat spectrum of Gaussian adiabatic primordial density fluctuations at the horizon due to quantum fluctuations in the scalar field driving inflation, which can generate all observable structures in the universe. Through inflation, the universe can act effectively as a graviton detector. It amplifies a quantum mechanical effect to where it can be detected as a classical, observable signal and may provide compelling empirical support for the quantization of gravity.
The particle, imagine it moving along a certain axis. In each case, there is always a maximum spin. In this case, a maximum and a minimum. Those can be thought of as the states where the spin is maximally along the direction of motion or maximally opposed to the direction of motion. A spin that way is considered positive along the axis, and a spin that away is considered negative along the same axis. There are no photons which are not polarized at all. Polarization is always perpendicular to the direction of motion. There's linear polarization, and I'm going to tell you now what linear polarization is. Linear polarization is not zero angular momentum along the direction of motion. It's a quantum superposition of the two possibilities, circular polarization to the right and circular polarization to the left. It has equal probability for being spinning to the right and spinning to the left. So doesn't that mean that it has, on the average, no spin at all? Yes, it does mean that on the average it has no spin. But if you measure the angular momentum of that photon, it will either be right-handed or left-handed. You will never measure a photon which has no angular momentum along that direction. If you send it through a plane polarizer, it can be polarized, let's say, along the y-axis, or it can be polarized along the x-axis. If you use as your basis of states the circularly polarized states, there are only two of them, so the angular momentum of the photon is either along the axis or along the opposite to the axis, and there is no photon which has zero angular momentum along the axis. The same is true of gravitons. Gravitons are spin 2 objects. If they were massive, they would have 5 states, but gravitons only have 2 states. A graviton moving down the axis with maximal angular momentum, that means 2 units of angular momentum moving along the z-axis, is mathematically the same as 2 photons, each with 1 unit of angular momentum. They could both be circulating in the right-handed sense. They could be both circulating to the left. What you don't have is a graviton which corresponds to a photon of right polarization and left polarization. Gravitons have only 2 states, maximal rotation in one direction, maximal rotation in the other direction, and mathematically a useful way to think about spin 2 by combining 2 spin 1s. There's a whole field of study which studies Feynman diagrams for gravitons by thinking of them as, roughly speaking, squares of Feynman diagrams for spin 1 particles. But mostly I think it's trickery. There's no real sense in which a graviton is 2 photons. It's just for combining the spins that it's useful. I can't think of any other sense in which it's particularly useful. There are no other quantum numbers. What other quantum numbers does a photon have? Or a graviton? Doesn't have anything else. Has momentum. Has momentum, has energy, and has spin. So, doesn't have charge, doesn't have baryon number, doesn't have anything else.
Remember, a quick look at Kepler's third law reveals a common universality with our time loop. Therefore, we can use the two-body problem to work out the relationship between the H plus and H minus potential states of the Higgs particle and use the M violation to relate the Higgs field to a gravitational field, thereby quantizing gravitation and bringing it into the standard model. Photons have spin 1 and 0 charge. Since photons can couple with both particles and antiparticles, we will maintain its time reversibility. We will let the slight inherent asymmetry between forward time particles and reverse time antiparticles correspond with the small angle theta corresponding with the axion. The axion has spin 0 and charge 0. The axion is also associated with time reversal symmetry. This allows us to make a Feynman loop of an axion phase fluctuation in and out of the vacuum. However, what we will do is take time reversibility of photons into consideration. The time reversal symmetry associated with axions, and the soft time symmetry breaking associated with small angle theta. This allows us to intermediate photon scattering with a cold axion background field.
Now, it would be natural to ask whether this is a Bose-Einstein condensate. Imagine you have a few states that are highly occupied. It happens that this has actually essentially no entropy. But if you allow interactions, what will happen is that you will increase the entropy by putting all the particles practically in the lowest energy state, but a few particles absorb the energy and they form a thermal Planck spectrum above. So the ground state has no energy, has no entropy, but the entropy is in the thermally excited states, and the entropy goes up from going from here to there. So the big issue then is, do they thermalize? They do thermalize because of gravity. 10 to the 61 axions are in the same mode, and the wavelength of this mode is a light year. These axions, their gravitational fields all add up because of the long-range nature of gravity. And this mode carries a big gravitational field, and so they get thermalized by gravity. If you try to estimate the relaxation rate by gravity at the QCD scale, you find that it is much shorter than the age of the universe. And when you reach a temperature of order 100 eV, 500 eV, photon temperature, the gravitational interactions amongst axions are sufficiently fast, and then they should form a back. What should happen is the whole universe will want to go into the lowest energy state, and you have a coherence length of order the horizon.
We can bring in a time reversal asymmetry, intermediating photon spin asymmetrically with a spin 2 particle that has parity and time asymmetries, the graviton.
So how about gravitation? Is it in fact like electrodynamics? Do gravitons actually exist? We don't know. There's first of all what I would call the orthodox view, the view of all the experts, which is that in fact there do exist gravitons and that they obey the equations of quantum gravitation, and they have the same kind of behavior as the photon, except that it's harder to observe. So that's the first possibility. The second possibility is what I call concealment, that quantum gravity exists, but it can never be detected in the same way that the quark exists, that there's a particle called the quark, which everybody believes is real, but it can never be observed.
This picture, taken from the L3 experiment that left, shows the body and soul of QCD in a very tangible form. And these sprays, when you look into them, consist of strongly interacting particles. However, there's a missing ingredient. So there was a leap of faith here. That is identifying the energy and momentum carried by these conglomerates of particles with the energy and momentum of some underlying structure that you don't actually see, the quarks and the gluons.
In point of fact, you can never see a quark by itself. All you can see is confined systems in which the quarks are hidden. That's why we call it confinement. So that's the second possibility. And the third possibility is that quantum gravity is nonsense, that gravity is a purely classical phenomenon. It is some kind of statistical property which only belongs to matter in the large and not to matter in the small. So there's no such thing as the gravitational field of an electron, that in fact it's only a collective property of matter in bulk. The second equation is for a single graviton. So the energy of a graviton is at most this quantity E sub s. Because, again, of this large velocity of light, the Planck length is a very, very small number, 1.4 times 10 to minus 33 centimeters. So that is, in fact, then the standard distortion produced by a single graviton. It's the fact that that's so small which makes gravitons hard to observe. And that tells you then this coherent conversion doesn't work. That if you have graviton and a photon going at different speeds, they're not going to be coherent with one another. So the coherent conversion simply fails.
In Freeman Dyson's lecture paper titled, "Is a Graviton Detectable?" he discusses on page 13 the conversion of gravitons into two photons. The field B must be very strong to obtain a reasonable rate of conversion of gravitons to photons. A detector with the same design has been used in a real experiment to detect axions. They have not yet detected any axions.
By the way, the people at CERN actually use this as a device for detecting axions. There was an experiment done at CERN looking for the coherent conversion of photons into axions, axion being a hypothetical particle with mass zero, which might exist and be detectable in this way. And so they did the experiment and also got a null result because they were not looking for gravitons.
On page 14 through 15, under nonlinear electrodynamics, Dyson states, "There's an important disturbing fact, the nonlinearity of the electromagnetic field caused by quantum fluctuations of electron-positron pairs in the vacuum. It follows that the photon velocity v is not equal to c, but is reduced by a fraction. Since the graviton field is not affected by the nonlinear electromagnetic interaction, the graviton velocity is precisely c, and the photon and graviton waves will lose coherence after traveling for a distance." What becomes apparent is that we can argue that the graviton and photon undergo different rates of the passage of time. Since the photon is theoretically slowed down by quantum fluctuations in the vacuum, and the graviton is unaffected, in this case the graviton is in the infinite momentum frame and the photon is not. This would be consistent with the argument that the vacuum has a higher rate of the passage of time. This would indicate that the graviton may be unaffected by electromagnetism, though it is affected by acceleration or gravitational fields. The graviton carries passage of time asymmetry. An axion phase fluctuation in the vacuum, collectively with other axions, acts as a Bose-Einstein condensate permeating the cosmic background. This phase fluctuation has two states, which we can associate with blue-shifted and red-shifted photon scattering.
The cross-section for photons are hitting each other is really, really small. It does make a tiny, tiny change in the equation of state. It actually depends on the temperature and density. If the temperature and density are high enough so that when the photons collide, they can produce electron-positron pairs, then the equation of state will change. And that's the main effect. But that's exceedingly high temperatures, way, way, way beyond. And the temperatures that we're talking about are very low. By comparison with that, they're very, very low. So the cross-section for two photons to interact and to scatter off each other is negligible. But it in principle would affect things, yeah.
Even though energy is conserved and photon propagation is time reversible, the blue shifted corresponds with popping out of the vacuum, perpendicular to the infinite momentum frame, and the red shifted corresponds with fading back into the vacuum, parallel with the cosmic horizon. The asymmetry in hue between forward and reverse photon scattering has to do with the arrow of time. The shift between forward time particles and reverse time antiparticles is preserved by the axion and propagated by the graviton. We can account for photon-graviton coherence, similar to how the passage of time can be used to account for the vacuum catastrophe, where there is a difference between rates of the passage of time.
Famously, if we just use the degrees of freedom within the standard model, it doesn't quite work. The couplings don't quite unify. However, If we extend the theory to include masses of order 10 to the 2 to 10 to the 3 GeV, it works much better. What is the exact statement relating observables to theory, and how accurate is it? We can just use the one-loop expressions, the first order, lowest non-trivial order expressions for how the coupling constants vary with scale. And then it's a matter of very simple algebra to prove that if you take the differences that are due to the evolution of these different guys and multiply by the correct beta functions or coefficients, the prediction of unification is that at some large m, they all become equal. And then the expressions in these deltas, and these differences of deltas, just reduce to observable coupling constants at low energy. This calculation gives two outputs from the three inputs of the observed couplings, and the outputs are the value of the unified coupling and the value of the unification mass, and those are the values. You get a reasonably good, but not perfect, unification also with gravity. Gravity, of course, famously, and this to me is the main problem with quantum gravity, it initially starts out terribly, terribly, terribly weaker than the other interactions.
The unification of mass corresponds to some arbitrary value m. The passage of time component and the linear time component correspond to different familiar physical quantities. The linear time component corresponds with the age of the universe, and the passage of time component corresponds with the Hubble parameter. If we examine the basic expression for the Hubble constant, where v is the redshift velocity and d is the proper distance, we get the following. If we cancel out the spatial components of the expression by dividing out the proper distance from the redshift velocity, we get the following. We are left with the Hubble parameter equaling the inverse period of time component of the age of the universe corresponding with linear time.
Whatever kind of nice equation of state you have, for most equations of state, the Hubble constant today is related to the inverse age of the universe. And saying that this is negligible compared to this, 1 over a squared then is h squared, and h squared is 1 over the age of the universe squared, it's telling us something about the size of the universe. It's telling us the size of the universe is basically the age of the universe. Now there is a speed of light in here. A is measured in length, t is measured in time. The size of the universe is about equal to the distance light will travel in the age of the universe. So this is what was expected to be true on the basis of cosmology 40 years ago.
If we re-examine the Friedmann equation, focusing in on the vacuum energy density, ρ0, the energy density of the vacuum can remain constant over the history of the universe relative to the infinite momentum frame while having a gradient relative to the inertial frame. The energy densities associated with matter and radiation become expressions of the gradient.
And now the latest on the Big Bang.
A shockwave hit the foundations of cosmology recently. Einstein believed that gravitational waves, a kind of ripple in space-time, did exist. The findings at the South Pole appear to confirm his theory. The big announcement came just months ahead of this autumn's release of polarization data from the European Space Agency's Planck satellite. The question now is whether the gravitational wave signal really did come from the dramatic first moments of the universe, the period known as inflation, or did they come from interferences such as galactic dust?
There are still some significant question marks about the bicep measurement, which need to be answered.
The reason for the excitement is that gravitational waves could teach us a lot about the universe.
What was previously heralded as the most important, cosmically significant scientific discovery of the decade has just been dealt a crippling blow, and it's all thanks to a patch of space dust. The BICEP 2 telescope was busily scanning the background radiation which permeates the entire universe. Scientists were looking to detect tiny fluctuations in this radiation, evidence of a phenomenon known as gravitational waves. In March, scientists announced they had found patterns left behind by those waves. The discovery was presented as proof of cosmic inflation theory. But once the hype faded, doubts began to emerge. One of the most damning critiques came Monday from a large team studying data collected by the European Space Agency's Planck spacecraft, which has been systematically examining the distribution of cosmic dust in the night sky. Their analysis shows distortions that were attributed to gravitational waves might have just been dust particles all along. To be clear, the new study doesn't completely sink the original findings. The BICEP and Planck teams are currently working together to figure out how much cosmic interference might have fouled up the BICEP 2's measurements. But it's a kick in the teeth for proponents of cosmic inflation theory. One cosmologist involved with the Planck study told Quanta they more or less assumed that they could find a piece of the sky with low dust emission, and the Planck results shows there is no part of the sky where you can ignore the dust.
Either the gravity is wrong or one of the physical laws are wrong too. Some physical law that's involved.
Because I'm not arguing at the moment that the physical laws are wrong. I mean, you would agree that one has to push it through along these lines.
Yeah, the best way to progress, I always think maybe, is to try to be as conservative. That's what Wheeler always said. To try to be as conservative about the physical laws as possible in explaining the phenomenon. And if you continuously fail, then you gradually realize you got to change something.
But maybe we're stuck in that. Maybe we should have a kind of cosmic humility. Maybe there are things we could have seen 5 billion years ago that we can't see now. Maybe we are limited in the fundamental questions we can ask by our circumstances. We don't know.
Rather than representing the history of the universe, the Friedmann equation represents the history of quantum fluctuations, particle pair production and annihilation over various periods of time at various phase transition points relative to our inertial frame.
A one-shot world is a kind of goal of cosmology. By one shot, I mean the whole thing happens once and it doesn't recur. This term is a kind of source. It's creating new things. This is a sink. It's eating up things similar to the equation which you would have if you had a source of fluid on one end and a sink down at the other end, so that the fluid flowed from left to right, from source to sink. It creates vortices endlessly. Those vortices, however, have a very definite sense of time, a flow like this.
The best analogy for this is a shepherd's tone.
I want to talk about the shepherd tone. It's a sound made out of multiple sine waves that play a trick on us. See, what they do is continuously rise in pitch, and then every so often one of them drops down an octave. But our brains don't perceive that because the other two continue rising and cover for it. The sine waves take turns dropping down an octave, producing a sonic barber pole, a noise that appears to keep rising in pitch forever and ever without ever actually going anywhere.
Though the universe appears to be an accelerating expansion, it actually is just repeating probabilities of quantum fluctuations, starting on one side of the ground state and ending up on the other.
A canonically normalized boson field, whether graviton or axion, during the inflationary phase, during the de Sitter expansion, feels, crudely speaking, an ambient temperature, the Gibbons-Hawking temperature, which measures the scale of inflation squared divided by the Planck mass. And that makes fluctuations in these things that get imprinted. For axions, that translates into jitter in the theta zero parameter, and thus ultimately into isocurvature density fluctuations. Isodensity curvature fluctuations are fluctuations in the dark matter density that are uncorrelated with fluctuations in temperature or baryon number density. When all things fluctuate together, that's called adiabatic fluctuations. Those two kinds of fluctuations have observably different effects on the cosmic microwave background anisotropies, and one can distinguish them. So the upshot of all that is that inflationary axion cosmology would be falsified if we saw the gravitational waves indicating a large value of the inflation scale without seeing the isocurvature fluctuations that would be entailed for the axion field. It would certainly help if we still have a dark matter problem after the LHC and WIMPS searches do their work. So keep going and keep not finding anything. Or especially if we actually discover the isocurvature fluctuations without gravity waves, we'd have to blame them on something, and axions would be the obvious candidate.
Ideas for what the dark matter might be have sort of had at least the luster taken off them, or in some cases just been ruled out altogether. So-called WIMPs have been very popular and still are perhaps the leading candidate in most people's minds, not mine. People have done very elaborate experiments of many kinds now to look for WIMPs without finding them. So axions are just about the last man standing. Particularly interesting and I think encouraging about the axion is, first of all, that the theory has really been unrivaled for decades now. People have not come up with alternative explanations for the problem that the axion solves.